So try your best to make sure that you've had access to the course so that you can be able to access the materials. Watson, kindly turn off your mic. So yesterday we had a mental map assignment, which we did. We had a mental map assignment, which we did, and you are meant to go and upload your mental map picture. So just take a picture either using a phone or something like that, and then go to the Unit 1 section of the materials, and under assignment, try and upload your assignment at this section. So you can upload your assignment here. I'll be posting more assignments today, covering what we covered yesterday and what we have covered today. So endeavor to utilize the after lunch session to try and complete a number of assignments that you will be receiving in the platform. Okay, so thank you. Let's go to continue. Now, just a quick recap of what we did yesterday. We handled a number of items in our yesterday's lessons. So yesterday we covered quite a lot of things. First, we covered aspects of what GIS is, and also we handled the components that are available within the GIS. We talked about the hardware component, the software component, the people component, the procedure component, or rather the algorithms that you use for analyzing the data. And of course, the major part of the component of the GIS is you and the data. So data is very key for GIS. Without data, GIS becomes totally irrelevant in terms of the use. Then also we handle issues of spatial data models. We looked at different types of spatial data models. And in those spatial data models, we focused a lot on vector data model. And today we are going to dive more to look at what we call the raster data model and object-oriented data models. And then later we'll dive into a little bit tricky type of stuff on coordinate systems, map projection, and datums. And then summarize the day, hopefully with map scale features and designing a map. In tomorrow's session, of course, we'll continue with spatial databases, looking at aspects of spatial analysis and geoprocessing tools. And then summarize the day with the GIS application, looking at the case study in natural resource management. So we still have quite a lot. As you can see, the list is still large. So let's try to dive in as quick as possible. So yesterday we looked at a lot on vector data model, topology, and so forth. Now today we want to focus a lot on the raster data models. So what is a raster data model? A raster data model is commonly associated with continuous field conceptual models. So yesterday we talked about a vector data model to be discrete, okay? It looks at discrete objects or features of the earth. But now in the raster data model, you're looking at things that deal with continuous sort of surfaces. It's not a discrete surface. A discrete surface is the one that has a clear defined boundary between one feature and another. In the continuous one, there is a merge in between. Like I mentioned, you cannot move from ice to fire. There should be a clear shift or a slow shift between what is very cold to what is very hot. And that's why temperature is one of the models, or rather one of the examples that are raster based models, because they are continuous in nature. So geographic space is represented by array of cells. So for raster data, you find that an object or space or a surface is represented by array of cells, which are also called pixels. And these pixels are arranged in row and columns. And for each pixel, again, it must have a value that represents the information. So yesterday I made some small sketch, and this sketch is now quite clear in this. So for example, we have this image on our right, and this is an image that is taken by, let's say, a satellite. You can also pick this image if you've used a drone to capture maybe an environment or a surface or a forested area. And then you'll be able to see that when you zoom into a small section of that image, you'll see that this image is composed of squares. Just like a digital image, if you take it using your camera and you zoom in so much in details, you'll be able to realize that the image that you're seeing is composed of squares. Now, inside these squares, the reason why these squares are looking like this, and I'm going to explain using this, is because each of them has got a value. And the higher the value, in this case, the darker is the green. And if the value is less, then the greenness is lighter. Okay. So for example, value 1, if you look at value 1, and then you look at the color, Andre, we are recording this meeting, and this meeting shall be shared. The recording shall be shared with you. I'm going to show you where you can be able to access them. So kindly don't ask to record. Thank you. So you'll find that this cell is light. It's having a lighter green because the value is 1. And this cell is having a darker green because the value is higher, and it's 9. And value 3 is a little slightly darker than value 1, as you probably see in these both images. Now, also we'll learn more in details that things like points, lines, and polygons can be represented in a raster data model as well. It doesn't mean that a line, a point, and a polygon is only represented as a vector data. That's not true. It can also be represented as a raster data. And that's why in this image, if you look at it clearly, you'll be able to see that the roads, we can be able to see the roads also being represented. The river is also being represented, and yet those are linear features. What we're trying to say is that for certain objects that are discrete, what I mean by that is that there's a clear difference between the boundary of a road and probably the land that is not a road. So for such objects, it's better to represent them in a GIS environment, or to model them within the GIS environment using the vector data. Now, for example, if you look at the challenges that raster data will have, if I decide to draw a line using a raster using a raster data model, you'll see that in between the connection of the pixels or the squares, certain sections are large, certain sections are small, okay? Yet we know very well that a road, there are sections that are small, but they are not abrupt change from big size to small size. So for example, if you look at this section of the cell is very tiny, and then this section of the cell, the road is very broad. So that doesn't give a very clear representation of what is actually available on the ground. So for example, if you want to measure the road, the width of the road, it's better to measure the width of the road when it is in a vector format than when it is in a raster format, because you'll have this part of the road will be thicker, and then between the cells, the road will be smaller. Then also you'll see that this road, instead of it going probably like this, if we were using a linear feature, you'll see that at this section, the cell is empty, and at this section, the cell is empty. So the direction of movement of the road, or the meandering of the road, or the corners, the junctions in the road cannot be well represented in a raster data format. And I'll show you more examples of how discrete features are better represented using a vector data other than using a raster data model. But none other than that, we see that these values of each pixels on a raster, it can be an integer, okay? An integer means 1, 2, 3, 4, 5, 6, 1,000, 10,000, 1 million. So those are integers. They're just single whole numbers. They're just whole numbers. But now, if you decide to have a decimal point, let's say 1.3, 1,000,000.6, or 100,000.467. When you decide to do that, then you're going into what we call the floating points. So the floating points are numbers that have decimal places in between them. Then we have what we call alphanumeric. Alphanumeric is something that has a combination of a letter, let's say A, and then 0, 5. Okay, so the alpha part of this alphanumeric is the letter A, and then the numeric part is 0 and 5. Okay, so alphanumeric, so these cells can either be 1A or 1C, and this can be 3. That means the values of a raster is in an alphanumeric form. Now, as I mentioned, raster datasets, because they are continuous in nature, can help model certain aspects of the Earth features using them. And the examples are, for example, the elevation, the precipitation, or rather people know it so much as rainfall, the slope of an area, the pollution concentration. Let's say if you're looking at carbon dioxide concentration levels in the atmosphere, we use raster data sets to represent or to model them inside our computer. Remember, what we're trying to do is we are saying out there or in real life, we have components that are in an environment, components that we know about them. But now we want to make sure that we interpret it into a computer, or we capture that information inside the computer. And then when we capture it and represent it inside the computer, we can be able to manipulate that information. We can be able to modify it. We can be able to run a prediction. We can be able to manipulate it as much as possible. If, for example, we have pollution on top of our atmosphere, the only way we can manipulate it is by, I don't know how you can, it's probably going to the atmosphere, capture it, capture it maybe in a jar, go to a lab and start manipulating the carbon monoxide that you've captured from the atmosphere. But what if you can't do that? What if you don't have the resources to fly out there, up there, capture all the carbon monoxide and start manipulating them? So the reason for all this is because we want to be able to manipulate or work with that kind of data inside the computer so that you can generate some models. We can be able to come up with a decision of how to maybe reduce the concentration of a pollution and so forth. Okay. Now, continuing on raster data, raster data sets have a cell dimension. So we mentioned that a raster data model is composed of cells or pixels. Now, or squares. Now, each square we have said has what we call a value. This value can be an integer, it can be a float, means it has a number with a decimal point, and then it can be alphanumeric, meaning it has a letter and a value or and a number. Now, in addition to that, raster datasets have what we call cell dimension. And this dimension helps to define, or it is defined based on the edge length for each square cells. So for example, you will be able to see that a dimension of a cell can be 30 meters, it can be 100 meters, it can be 1 kilometer. Now, the image that you'll probably see in your camera, if you look at the back of your phone, it will say something like megapixels. So that means your camera has an ability, if you capture an image and you know the area of the image, then you can be able to multiply or divide that by the megapixels of your phone, the value that megapixels, and you'll be able to know the dimension of an image. So each image has what we call a dimension. Now, in this case, when you move from this point to this point, that will be the dimension of that cell. Now, the dimension to make has to, because it's a square, it has to make an area. So it means you have a dimension here would be 30. And then also here, it would be 30. So 30 times 30, this cell would be 900 square meters if the units of measurement is in meters. So each of these cells has a dimension, meaning there is 30 here and there's 30 this side. Okay. Now, the cells are usually oriented parallel to the X and the Y axis, as you'll probably see here. And the coordinates of a corner location are specified. Now, even for the previous cell that we had, it had a dimension, and the corner coordinate is also available. So look at this. Each of this is the image section that was depicted from here, all right? But you'll see that at the edge, there are two values, okay? In this case, it is 0, 0, 5, 0, 0, 5, and 5, 5. So it means if I had made a drawing on X and the Y axis, this is Y, and this is X, okay? Now, we all know from the high school that where the Y and the X meet is a 0, 0, right? So it means this would be 0, and this would also be 0, okay? Now, what we are seeing is totally opposite of what is actually what we used to remember as in the number line. So as you'll probably see, this cell, instead of the 0 being on the bottom end, it's actually on the top end, okay? And that is not by mistake, because the array or the dimension of an image, its origin is in the top right, top left corner. So this will be top left, and this will be top right, this will be lower right, and this would be lower left of an image. So, but the concept is still the same. The only difference is that where the zeros should have been is now on the top, okay? So it means if this was 0 and this would be 5, okay? And this would be also 5, okay? So in other words, this section would be 0, 0, which is opposite of the other, okay? And basically that. So I could also decide to say, let me put my number line like this. It's still a Y and it's still a X, okay? Meaning now it is normal. The 0, 0 is this side, and then you'd have a 5 and a 5. The problem is that in a number line, as we used to know, anything below 0 would be a negative, okay? So you can either flip it the other way around, or you can flip it this way, but make sure that the values are not actually negatives in this case, but still in a number line, it will still be the same. So that's the same concept like we have seen in this section. We have the X and the Y, but remember, it has been flipped. So in other words, this would be the lower left cell, which would not be necessarily 0. The 0 is in the top left cell. And then this would be the higher value, in this case would be like 5 or something like that. Okay. I hope I've not confused you. But going further to understand the dimension of the cell, here they're saying that the number of cells in a raster dataset depends on the size. We have just mentioned that, okay? So if you've taken a picture of a whole house, that will be the dimension or the size of the picture. It is a whole house. Now, if you decide to take a picture of only one section of the house, let's say only the front end of the house, you realize that the picture of the house will be smaller than the picture of a full house, okay? Now, here we are saying, okay, the dimension or the size of the house just that you've taken from the picture of the house that you've taken from a section, let's consider it to be this size, okay? So if you decide to say the dimension of my cells will be 100 meters, this will be how the cells. So basically you'll have 4 cells. If you decide that, I'm not saying that you decide, it is what the quality of your camera is deciding, okay? So you can't control, you can only control the quality of your camera by buying an expensive camera. If you have a very simple phone, which I don't want to call it cheap, but a lower price, it will not have a very good camera like a phone which is of a high price value. There are people who buy phones because they are interested in the quality of the pictures they take. I've heard people talking about iPhone having the best quality pictures. And then those who have Samsung also keep saying, no, 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 no. Samsung has the best quality picture. What these manufacturers have done is to say, for each pixels, the dimension should be smaller. Okay? So when the dimension of a pixel in your camera is tiny, like nanometers, like so tiny, then the pictures that it will have will be also more clear. Okay? So here we'll see that if you decide to have a dimension of 100 meters, then you only have 4 cells. If you decide that your dimension should be less, and let's say it is 25 meters, then you'll have 64 cells. Okay? So the smaller the dimension, the higher the number of cells that it will have. But now, the more the number of cells, the heavier or the picture or the heavier or the larger your image is going to be. So for example, if your phone takes a very clear picture, it means first of all, the cell dimension is very tiny, but also the number of cells that that picture will have will be very high, in millions. Now, because of that, the picture is going to have a high number of MBs in terms of the storage. So a picture that is maybe 100 meters in dimension and having 4 cells might be maybe 1 MB. Okay. MB means megabytes. Okay. But this one could be, I'll just exaggerate it. It could be 1 GB. Okay. This will be 1 gigabyte instead of 1 MB. So it means in normal circumstance, this image is lighter, but this one is heavier. And the reason for that is because, one, the dimension of the cells are very tiny, but the number of cells are very many, making it very large. So we'll talk more on issues of resolution and the sizes of the cell and the impact they have in different Landsat or Sentinel images or satellite images in general. But the concept is still the same as I've talked here. So raster layers may also have associated attribute table. Now, this is very important. What we have been concentrating on here are basically the values that are in a raster data. And also too, we have been concentrating on aspects of coordinates. So it has the upper coordinate, the top left coordinates, the top right coordinate, the bottom right coordinates, and the bottom left coordinate. But now what we are saying here is that in addition to the values that it has, it also has an attribute table. Okay? Now, what we are trying to say is that if in this case, these are alphanumeric sort of values that this raster is having. So in this case, any value, any raster cell that is having a value A has an attribute table linked to it. So in other words, anything that is A will have a class of 10, and the area for it would be this. If it is about pollution, this could be the concentration. So if it is concentration of carbon monoxide, you would add another value here in this attribute table. And then we would have the concentration value of carbon monoxide for each of these cells. Let's say A would have a value of maybe 10, 10, 10, and then anything that is B would have a concentration value of carbon monoxide to be 15, 15. If we have a C, or in this case we have a D, then the carbon dioxide concentration would be maybe say 25. Okay, so each of these values are linked to a certain cell in here. Okay, so B is linked to B, and then E is linked to E, and anything in C is also linked to C. So just by looking at an image, you're seeing the cell values about it. However, in addition, in the back of your mind, you should ask yourself, okay, like if you take an image, part of an image might, let's say you've taken an image of the door of, okay, a section of a building, or a section of the front section of a building. You'll probably see that part of the image is having a door, part of that image is having the window, part of it is having the wall, and part of it is a roof. So that means parts of that image that is a roof is going to have a different cell value, and then part of it that is having a door will have a different cell value and the wall. And that's why you can see the differences between the parts that are in the image you've taken using your camera. It's because of the different values that each cell is having about them. Now, just as with topological vector data models that we looked yesterday, features in the raster layer may be linked to a row in the attribute table, and these rows may describe essential non-spatial, okay? The word non-spatial is very important, characteristics of the feature. So this time we're not talking about the coordinate part of the raster cell, but we're talking about the descriptive information or the characteristics of that value of the cell. Now, now we have said, okay, this attribute table is related to this cell or this raster image. Okay, so in other words, there is a relationship between this raster data with the attribute table that it has. Now, this relationship can either be a one-to-one, or it can be a one-to-many. We are going to explain that in details. So what do I mean by a one-to-one relationship? So a one-to-one relationship means one cell has its unique attribute table, okay? So corresponds, or the correspondence is rarely used with the raster data sets because it's often would require an unmanageable large size of attribute table. So in other words, what I'm trying to mean is that for each of these cells, it should have its own attribute record. This one also should have its own attribute record. This one also should have its own attribute record. So it's a one-to-one relationship. Okay. Now, the challenge with it is that this attribute table, depending on how many cell values are here, should equate to the same number of the rows or the records that are in the attribute table. So for example, if 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is 100 by 100, which is 10,000, right? Now, in other words, this attribute table should have 10,000 records or rows. If this image is to have a one-to-one relationship between the attribute table and the raster. So you'll actually realize that that will make the table very large. Okay, you'll have over 10,000 rows for this attribute table for a one-to-one relationship. And probably for those who have worked with Excel and you have so many records or so many rows of, let's say, 1 million, you'll see that your Excel may not even be able to open. Or if it opens, it will be super slow. You'll not be able to, every time you change a record, it will take some time for it to refresh and all that. And you don't want something like that to happen. Now in a GIS, we decide to say, okay, let's have what we call a many-to-one relationship, okay? So a many-to-one relationship, in this case, we're saying, okay, anything that is 10, so these values, these ones, these ones, these ones, these ones. Do I still have 10 somewhere? 10 is here. Yes. Kindly mute your mic, guys. And keep your camera off. For example, you man, you're in the bathroom. Sometimes we see some of these things and we get shocked. Okay. I hope that's not being recorded. So a many-to-one relationship means all the values that are 10, like in this case, anything here, all this part of the image is having a single attribute table linked to it. Okay. So all those values are linked to one attribute table. Also, you'll see that anything that is 15, okay? And by this, it's not necessarily that 15 has to be together in that image. For example, here we are seeing 15 neighboring each other, but you might also find 15 is somewhere here. A neighbor of 15 cells are also on the other part of that image. Just like when you take an image of your front end of your home, you have two windows, for example. So you'll have one part of the image having a window and another part having a window, and then you have a door and so forth. Okay. So in GIS, for example, land use, you'll have the forest in one section of your image. Then also you have a forest in another section of your image. So it doesn't mean that 15 or the same value has to be in one place, neighboring each other all the time. It may not have to. So a many-to-one means there are many cells and one single record for that. Okay. There are over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and blah, blah. So many cells of a value 11, but there's only one row for value 11. And in most of the raster data sets that we use in today's analysis are a many-to-one relationship arrangement. So now that we have looked at a good introduction on raster and vector, let's look at the different comparison or the different strengths and the weaknesses that each of it has in terms of its characteristics. So in terms of the data structure, remember yesterday we talked about data structure. Data structure is how things are organized, okay? How things are organized. So in terms of the data structure, usually the raster data sets have a simple structure, but vector data will have a complex structure. In terms of the storage requirements, raster data often are too large, and I've mentioned that in terms of the dimension of the pixels versus the number of the pixels that it should have. If the dimension is large, then you're going to have fewer pixels. If the dimensions are very tiny, you'll have many pixels. Now, many pixels equates to the size, just like I mentioned in my previous presentation, that you can have a 1 megabyte image and you have a 1 GB or gigabyte image, just because the number of pixels are higher and the dimensions are smaller. Now, for storage requirements, vector datasets always takes in a very small space of storage. So when you're working with these two major or common models of data, there comes a time where you need to do a conversion. You want to convert from a raster to a vector, or you want to convert a vector to a raster. Now, in other words, when you're doing that conversion, the coordinates also get converted, and we're going to look at details of what coordinates are about and the coordinate system and all those effects, how it affects your analysis or your data. Now, for vector data sets, the coordinate conversion is very simple because the objects are discrete. However, for raster, like we mentioned that we have the corner coordinates. So when you do a conversion, those corner coordinates affects the different cells that are there, and then it makes the process very slow, okay? So maybe slow due to the data volume and require resampling. We'll also look at resampling in remote sensing when we are doing the remote sensing part. Analysis, easy for continuous data, simple for many layer combination. So most people say they understand that working with shapefiles are very easy, but working with raster data sets are very complex. However, as you keep learning in GIS, you realize that working with raster data sets are actually more simpler than working with vector data sets, especially when you're doing layer combination. Combining a rod and a polygon might be very, very difficult. But when you combine an image that is having a combination of rows, columns, and all those things, it will become a little more simpler. The spatial precision, the flow set by cell size. So basically what precision basically means is that, let's say you have a bow and arrow, okay? You have a bow and arrow, and then you have a target. Let's say this is a target. The first time you shoot the arrow, your interest is to shoot this point. The first time you shoot, you could have shot here. Another point you've shot, it could have shot here. The other point you shot, you could have hit this part, and then you could have hit the actual area or point that you wanted to what? To hit in your shots. Now, precision basically measures when you shoot it 4 times, how many times did you shoot at the right spot? So if the first time, if like now I've shot this 4 times and this is the arrangement, and if in another shot, this is the area I'm interested, I shoot this part, I shoot here, I shoot the actual part, and then I shoot somewhere here. So you realize that in this shot, in the first attempt, that would be my shot. In the second attempt, that would be the small section I will have concentrated on. So here the precision is very low. So low precision. And here the precision is high. Okay. Now, precision and accuracy are different things. So we'll talk about that probably in details later. Now, in terms of precision, the flow is set by the cell size. So if the cell sizes are big, then the precision will be low. If the cell sizes are small, then the precision is going to be high. Now, for vector data sets, it is limited, the precision is limited by the positional measurements. So the positional measurements are basically the coordinates that you are doing. But also, if you're using a GPS, there is something called the position accuracy, or some people call it an error, error of measurement or something like that. So what it's trying to say here is that if the accuracy in your GPS is 3 when you're taking a coordinate, and for somebody the accuracy was 10, the person with the accuracy of 3 is more precise, and when I say precise, I mean the precision, than the person with the accuracy of 10. Okay? Israel, kindly rename yourself. I see Israel's Galaxy. We need your names, complete names, because this is going to dictate the names that are going to be put in the certificate. So kindly make sure you rename yourself very well. Accessibility. So easy to modify or program due to the simple data structure. Like I mentioned, people think raster data sets are very complex, but they're actually simple. But for the vector data sets, accessibility is very, very complex. To display and visualize the product for raster data sets, depending on for example, if you take a picture with a poor quality phone, the image will not be clear, okay? But if you take with a high quality phone, or the phone that has large megapixels, then the picture will be more clear. So depending on that, images are better displayed using a raster data format, okay? But sometimes the discrete features like the roads and so forth will have what we call the stair-step edges. So for example, if I have a lake, okay, this is in a vector format. If it is in a raster format, it will have these edges. Am I doing it well? Maybe. I'm not sure. Probably not. So what they're trying to mean is these edges. They are called stepwise or stair-step edges in a raster image. But for the vector model, it will be a smooth boundary or a smooth area. Okay. So for in terms of display, vector data sets have sort of a map-like continuous curves, like I showed you, which is poor for the images. So depending on what you want to apply or the kind of data you're collecting, you have to decide whether you want to store it in a raster format or in a vector format. But also you realize that due to the limitation on our abilities to collect all the data sets, you might receive the data that you want to use in the GIS in one of these formats. You can either get it in a raster format or you'll receive it in a vector format. So depending on these characteristics that you've seen, you have to make a choice. Either you make a conversion from one model to the other, because each of them has its advantages and disadvantages. But also some may allow you to make a conversion, others will totally refuse. So in other words, when you're trying to learn some of these models, make sure you understand them in depth so that when you're using them in a GIS environment, you're well conversant with what you're doing. So in real life, these are some of the examples of features or objects that we can represent in terms of raster and a vector. Admin boundaries, parcels, land titles, or land parcels, all those ones are represented in terms of the vector data models. The roads, streets, rivers, and all that are better. Remember, I'm not saying it is the only way you can capture or store your data. The best way to do it for the roads, the rivers, and so forth, things that are linear in future, is by using the vector data model. Now, land use, elevation, pollution, rainfall, temperature, all those things can be stored or captured using a raster data model. Okay. However, you can also store or capture your land use using a vector data model, including, for example, elevation. We use contours to store a slope of an area or elevation in a vector data model. For us who studied in the Uganda education system in this, I think, senior 4 ordinary level, we did a lot of contour mapping in geography. So if you can remember, you'd see how the arrangements of the circles are and how congested or clustered they are in an image, and then you can be able to tell that this place is a hilly place. So elevation or slopes can be represented in a raster format, but also if you want it to be in a vector format, then you can use contours, for example. So we are not saying that everything that you're seeing here as an example must be the way they are. We're saying this is the best way to represent them when you're working with them in the GIS environment. Like I mentioned, the contours and the relief, these are all the same things. They're talking about the elevation of an area. One is in a raster format, which is a relief, and then the other is the contours, which is in a vector format. Okay. At this point, do I have any question? Before we jump into another section? All right, let's continue. In case you have any question, please just let me know. And you raise your hands, and then I should be able to pick you. Now, there's another very important spatial data model that we need to look at, and it's called object data model. So the object data model is an alternative for structuring a spatial data. And here the main goal is to raise the level of abstraction. Remember, what we are doing to represent real world objects in a computer is called abstraction. That whole process, you're trying to create an abstract of what is actually available in real world. So the main purpose of using object data model is to raise the level of abstraction so that the data objects or the Earth features may be conceptualized and addressed in a more natural way. So objects in this case are often geographical features, like I've just mentioned, with spatial and attribute data. Now we understand that if you're working with data that is in a GIS environment, it must have the spatial part of it that looks at the coordinates of the data, and then the descriptive information, which is the attribute data. So these objects must have the spatial and attribute data associated with them. And when you're using object-oriented data model, then you include all the things of interest and the relationship amongst them, okay? We have also said that you must include the relationship. Even the other two have a relationship. However, that relationship is a little bit more ambiguous when you're working with the data. You can actually be working with the data with whereby the relationship is not so much direct, okay? When you're using raster and vector, but when you're trying to work with object-oriented data model, then this relationship must be direct, okay? So to explain this more, things or objects or the geographic features might include the power poles, transformers. So let's use this example. For electricity system, we have the power poles, we have the transformers. So let's say we have the pole here, electricity pole. Oh, my drawing is horrible. So let's say we have here electricity pole. And then we have here a transformer. And then we have, of course, wires connecting from the transformer to the poles. And then here we have our house. So these wires are still going to the house. Inside the house, there's a meter, which these lines come and join to the house. And the customer's building, which is this one, okay? Now, let's look at how is this relationship done? That you have a meter. This meter is associated with this house, okay? And then this meter is linked to the pole, okay? And then the pole is linked to the transformer. Let's say the transformer is where the power is coming from. So if I have another house here, maybe for my brother, it also has a meter. It must link to this pole for it to get power. First of all, this meter is linked to this house and then linked to this pole. And this pole is also going to a transformer. So the way this relationship is so much clear. So for example, if I want to know, for this building, where is the power coming from? So I'll go to the meter, follow where the wire is going to the pole, and then follow that pole to the transformer. So that relationship is very, very clear and easy to understand. So objects in a GIS database, when you're using object data model, may be conceptualized in a diagram or a logical model of how they are related. So here, 3 types of objects are represented with owner, first object, associated with the parcel, second object, and the parcels are associated with the counties, third. So the counties are basically administrative boundaries, yeah? Now, you'll see that for the owner, there's an attribute table linked to it, okay? Let's say these are the titles or the names of the attributes. The first will be the name of the owner, the address of the owner, and the telephone number of the owner. Now, so there are 3 objects. There's a first object here, there's a second object here, and there's a third object. Each of these objects has individual attributes associated to them, okay? But what is very important is that there must be, for example, if you look at this owner, there's a name, address, and phone number. For the parcels, you're not seeing the name and phone number here. No, the attributes are completely different from this, that, and that. Yes, we have the county name, but this county name may not necessarily be the name of the owner. It's just the name of the county. Now, what is very important is that there should be what makes this relationship intact. And normally what in databases, we call them primary keys. So you'll have a primary key which can communicate between these 2 objects. And it may not necessarily have to be able to communicate directly here, but if it moves like this, there should be a communication between now the parcels and the county. So there should be a primary key, something that these 2 tables can understand when they are put together. So you'll read more on some of these concepts. We can't handle everything in the class because of time, but using this introduction, feel free to explore more and understand, watch some YouTube videos, and you'll be able to understand more details of what is here. Okay, someone's hand was up. I don't know whether I answered the question. Someone had raised their hands. Yes, Ibe. Ibe, you can go first. Ibe, can you turn on your mic and then talk?
Good morning, sir.
Good morning.
I wanted to ask, sir, it's about precision and accuracy. You said the both are different.
Yeah.
So I wanted to ask if either of which can stand alone, can precision stand alone, or do we need both accuracy and precision in order to get the perfect work? Since they are different, I want to know how they compensate each other. do they stand alone, or can one do? That's the question.
Okay. So precision and accuracy. Precision is basically accuracy can be achieved at one time. It's when you do a measurement and then you get it is 10, and the next time you measure it is 10, that is accurate. So that's it. Now, precision is when you do the measurement a number of times. Okay?
All right.
You do
Thank
the
you, sir.
measurement a
Thank you,
number of
sir.
times,
Thank you, sir.
then you obtaining the same value, then that means the measurements you're taking is more precise. So accuracy is a one-time measurement whereby you either qualify something to be accurate or not accurate. And then for precision, if you do something a number of times and you obtain the same value or different values, then you'll tell whether what you're doing was accurate, was precise or not.
All right.
I hope I've answered you. Yeah. So basically, one is useful in one aspect and another is useful in another aspect. Okay.
All right.
But if you can achieve, yes, but if you can achieve two at the same time, then that makes your work more accurate. Then you have high confidence in the things you are doing. Okay. And remember, in precision, you don't have necessarily have it. It measures really how close your measurement is to the accurate value. So basically, you first need to know what is accurate, and then you run a model a number of times and see the first time you run, how close is my measurement to the accurate value? That's the first time. Then you run it the second time. How close is my result to the accurate value? So remember when I made that drawing, the accurate value is the target. Okay?
Yes. Yes.
When I made that drawing like this target section is the accurate point. Now, you make the first shoot, maybe you hit here. Make the second shoot, maybe by mistake you've hit this side. So what is the distance between this point and the accurate value? It's the precision. Okay. So
Yes, sir.
Here the precision is very high. Here the precision is very low. Then here the precision is moderate, because the distance between the actual or the accurate value is larger for this and smaller for that. Okay.
Yes. Thank you, sir.
In my master's, I also had a lot of confusion on that, but later got to understand it more clearly during that time. Okay, so
Yes, thank
more
you,
about, you're welcome. So more about the data oriented, the object data models. We are going to have a typical example, and somebody mentioned that they're interested in hydrology, and this is really a classic example of how GIS is important in hydrology. Now, you have an object. Objects in this case will be the basin. For those who don't do hydrology, this might be a little abstract, but just follow and you'll be able to pick something at the end. So we have the objects which are basins. So basins have sub-basins, and then within the sub-basins we have a stream network and a station. So the stations are basically the power points. Now, in object-oriented data model, you'll be able to encapsulate complex objects that may be a combination of many different features, like we have seen here. This is a raster, it's a terrain, in other words, or the elevation in terms of how it is being represented, this basin. And then, so the basin is this whole big chunk, And then the subdivisions of the basin becomes the subbasins. And then you have those pour points. Right now they are looking here, but in actual sense, that is how they appear in the subbasins. So basically they are pour points of each subbasins. So object-oriented data model will help you to encapsulate this conceptualization, but also embed those complexities in a standard way. So it helps with the constraints by creating what we call the topological relationship, which we talked about yesterday, across the objects that may be represented. Now, that is what we are picturing. But inside a computer, there's these complexities which we are calling the schematic diagram. So this schematic diagram is trying to explain the relationship between these four objects in hydrological system in this case. So you'll have a basin, and in a basin, you'll have the attribute table for the basin. Okay, so first you have the attribute table of the basin, and then you'll also have a sub-basin which also has its own attribute table. You have the station with its own attribute table, and then the streamnet. The stations, like I mentioned, are power points in for each of these sub-basins. Okay. Now, after that, there is a relationship that each of it must have. So, for example, the sub-basins will have another attribute table called the basin feature. Now, the basin feature is an extra attribute table which the computer is trying to help it relate with other components like the watershed, the catchment, and the district. Okay, so if for example, in a catchment, there are a number of basins. Okay, rather in a watershed, there are many catchments. Okay, now these catchments can be in different districts. If you recall, for those who know hydrology, a catchment, or rather a watershed, can be too big. It can compose of many districts. So you can't say this basin has a relationship with a district, because first, relating a basin directly to the district will be able, because there are very many basins in a district, in one district. Now, you can't say each basin is in each district. Then you're going to still create the aspect of a one-to-one relationship. And that, remember, gives a lot of records and make the data too big for managing them in a computer. So what these people, what the software does is to split this information into separate tables so that there is something that is linking the basin to these other components. And what is linking them is called the basin feature, which has an ID. So this ID is not, helps to link this table with the basin, but also with the watershed. And that applies to these other ones. And as you look at the sub-basin, there are still more other components. For example, you have the outlet, the gauge points, and the dams. These are all linked to the root point ID. There is also a root line and a root area. So all those complexities are generated within the computer. For you as a human being, you might think it is too complex, but this structure makes it easy for a computer to manipulate your data. Okay? For example, if they split this district, like they do a lot in our country here in Uganda, you find a district has been split into 4. So if they split the district, it will be only the district table that will be affected, and all the basins will still remain unaffected. But if they were all in the same Excel sheet, let's say, then every time you split the district, you have to also split the basin, you have to also split the sub-basin and the watershed and all those things. So putting it in this way helps you to manage the data in a more accurate way. Some people are keeping their cameras on and distracting others. For example, Alan Bagonza. And you seem to be in your bed. I don't know what you want to show us. I think this is not right. So Alan Bagonza, can you turn off your camera? Thank you. So simply, that is what we are trying to mean when we're talking about the different object data model and how each of it gets related in terms of the schematic diagram. Okay, so we are going to first finish the coordinate system aspects. After that, then I think we'll be able to have ourselves a break. Let me just see what the time is. It's 10:26, started at 9. Okay, yeah, we're about to have our break. So let me rush through the coordinate systems and then we have our break. We come back and we wrap it up for today. So in the next segment, we want to look at coordinate systems, map projections, and the datums. Now, by history, in the 18th century, mathematicians argued that the centrifugal forces should cause the equatorial regions of the Earth to bulge. It's not my theory, it's their theory. Now, what they tried to calculate, and I'm going to warn you a little bit, we're going to talk a little bit of mathematics here, and don't be scared. When you're doing GIS, you just put a little bit of math, not really complicated mathematics, because the software has made it already easy for you, but you need to understand the concept, okay? Now, equatorial region basically means section of the Earth where the line of equator is passing. So just imagine in Uganda, we have the line of equator. I think also in Kenya, we also have the point of equator, and those from Congo. Which countries again? I think that's all. Congo, Uganda, Kenya. Those are the people in Africa that are having the line of equator passing through in African continent. For Congo, we just combine Central Republic, just combination of all that. So there's somebody with Techno BE8. Just check on the chart and rename yourself kindly. You have a Techno BE8. Kindly rename yourself so that we can be able to capture your name. Thank you. And you're the one with your video on. So kindly check and then rename yourself, please. Evelyn Sally, can you, Silali, kindly mute your mic. Thank you. So In this century, people said areas in equatorial region, the earth has been bulged. So in other words, the earth that we thought is round or is round like a ball is actually not round per se. It means the sections or the line, the point where the equator is passing is a little bit bulged out, or rather extend like a ball that has been pressed, okay? Instead of having a round shape like a clean circle. So they proposed that the earth would be better modeled by what we call ellipsoid. So ellipsoid is a circle which is bulged in the mid area. Okay, so it's like, it used to be round like a ball, and then it's slightly pressed. So the areas around the middle area get a little bit extended compared to the poles. So that's what an ellipsoid is. It's not a circle, but it's a circle which has a bulge areas in the middle. So a sphere in this case is slightly flattened, like I mentioned, at the north and the south pole. So in other words, imagine you put a weight here, or you press this ball from both ends, so that these areas are going to be a little extended out. Okay, so then you'll achieve the ellipsoid shape instead of a sphere. Now, what are we seeing here? If you measure the distance from the center of the Earth to the north and the south pole, you'll obtain a value called B. So this is the semi-minor axis. And then if you measure from the center towards the equator, okay, you'll be able to see that you obtain a value A, which is a semi-major axis. So why is it called semi-minor and semi-major? Is because this distance, because the ball has moved, or the earth is bulged a little bit, this distance is going to be larger than this distance. Okay, so that's why it's called, this one is called minor and this one is called major. Now, what is that factor of bulging? So the bulging factor, or the flattening factor, F, is equal to A, which is this, minus B, which is this, divided by A. So let's say this was 10 and this was 8. So 10 minus 8 will be 2, okay? 2 divided by 8 will be 0 point something, right? So that would be the flattening factor of the Earth at that point. Next, now that we have looked at an ellipsoid, which is a flattened sphere or a flattened circle, we want to go into what we call a geoid. Now, anyone who has done a survey here, please, in case I mention some things that are not correct, you'll forgive me. I'm not a surveyor, but basically we'll touch some concept that surveyors use when they are trying to do their kind of measurements in the field. So in GIS, a geoid is a model of the Earth's gravity, or the Earth's gravitational field, that is used to define the shape of the Earth's surface. Okay, remember there is an aspect of the gravitational field. Okay, there's an aspect of a gravitational field, and then it is used to define the shape of the Earth. Okay, So a geoid is an irregular surface that closely approximates the mean sea level, taking into account variations in the Earth's gravitational fields caused by differences in density of the Earth crust and the mantle. Okay, so the gravitational field differences is coming into the play because of the differences in the density of the Earth and the mantle. Okay, a geoid is important in GIS because it provides a reference surface for measuring elevation, the heights above sea level. And when using geographic coordinate system in GIS, elevations are typically georeferenced or are typically referenced to a geoid. That's confusion. Okay. A geoid is important to provide a reference surface for measuring elevation and height above sea level. However, when using GIS, elevations are typically referenced to a geoid. And this is often a difference from the Earth's ellipsoid or other reference surfaces. So a geoid is not an ellipsoid. It's different from the ellipsoid or the reference surfaces. And we are going to look at an image or a picture that has a geoid, that has an ellipsoid, and that has the conceptual as spherical surface. And then we'll see the differences between them. So to accurately represent a geoid in a GIS, it is necessary to use a specialized model, what we call a geoid model. So this model has been developed through precise measurements of the Earth's gravitational field. So when you look at a geoid, equate it to gravitational field. Gravitational. I'm writing like a child, gravitational field. Okay. So what we're trying to say is that there are two things. The Earth, we all conceptualize it to be round. It means it's like a sphere. Some mathematicians decided to say that, okay, the Earth is round, but it is bulged at equatorial section, meaning it is not actually round. It's an ellipsoid, okay? But other people are also saying there is an aspect of a gravitational pull, or rather the fields, that come into play and they make the Earth not necessarily a sphere and not necessarily ellipsoid. So ellipsoid means the difference between a sphere and ellipsoid is that it is a bit bulged a little, so it's not a complete circle. But a geoid is saying, no, in addition to it being bulged at the equator, the mean sea level or that line is not actually a straight line. What I mean is, let me draw this. So initially we thought that the Earth is round. Forgive my sketch. So it means the Earth is a sphere. Okay. Now, later mathematicians say, no, the Earth is actually not that very round, but it's bulged at the equator. So it is not round. Now, This is ellipsoid. Ellipsoid. Okay. But later people say, oh no, the earth is not smooth like the way you're saying here. This line is not that smooth. The earth, yes, it is an ellipsoid, but there are sections that are higher and others are lower. Okay, so just imagine the lakes, imagine the mountains. So even though we had thought, just 1 second, I pick a different color. So this would be the ellipsoid of the earth. Okay, but for some sections, for the mountains or hilly areas, this area is higher, and for the lakes and the seas, this area is lower. Oh. So instead of it having a smooth surface, it is not, because we have higher areas and we have lower areas. So the lower areas could be the lakes that are deep, and then the seas or the oceans, and then the higher areas will be the mountains or the rocks and all that. So this is now a geoid. Okay, so you've seen the difference. We moved from the sphere to ellipsoid to a geoid. Now, to finalize with this part, these models are typically based on the global satellite data and can be downloaded as geoid grids, which can then be incorporated into a GIS software for use in elevation calculation and other spatial analysis. Now, people who do surveys, I'm sure one of you have seen them in the roads construction. They have something, some machine, which is tripod, and then they keep looking at something there. I think it's called a total station. I don't know what, something like that. So what they're trying to do is they are trying to capture the elevation of an area. For surveyors, you'll forgive me if I'm messing up. They are trying to capture the rise or the elevation of an area. And that is helping them to tell, to first of all, capture the coordinates of maybe what they're measuring, or the plot or the road or something like that, the rise of the road, so that they can measure the slopes and all that. I'm just thinking loud, but probably that's what they're doing. But now you understand what a sphere is, what an ellipsoid is, and what a geoid is. So this image that you're seeing here is the actual look of how the earth is. There are areas, it is not smooth like the way we thought. There are areas that are lower and there are areas that are higher in terms of its shape. So depiction of the Earth's gravitational field, or the gravity field, as estimated from the satellite measurements. This shows the undulation greatly exaggerated in the Earth's gravity, and hence a geoid. So ellipsoidal, orthometric, and geoidal heights are interrelated. So I told you, I made a drawing earlier that you have an ellipsoid, you have also a geoid, and then you have a sphere. So these things are all interrelated. And this diagram is going to explain that. Note the values for n, which is this. Now, let me first explain what you're seeing. So the undulated surface that you saw earlier is this one, the geoid. So this will be the geoid, okay? Then the smooth bulge of the earth is ellipsoid. So this will be the line. Now, the Earth's surface, which we thought or we think should be, is this one. Okay. Now, if this is what we want or what we think it is, the height between the bulge or ellipsoid is h. It's called ellipsoidal height. And surveyors, you'll forgive me because I did GNSS in my master's, and it was horrible. It was very hard for me. So if I'm explaining things wrongly, kindly help me out. Okay. Feel free to put up your hand and say, Thomas, there's just this part which you've missed. This is it. Okay. And I'll agree. So ellipsoidal height, the height between the bulge shape of the Earth and the actual ground surface, is equals to the height between the geoid and the surface of the Earth plus the plus sorry, excuse me. So let's continue. So this height, this one, which is ellipsoidal height, is orthometric height, which is the height between the geoid and the surface, plus the geoidal height, which is the height between ellipsoid and the geoid. Okay, so that will be ellipsoidal height. I'm laboring to explain this because the n, which is the geoidal height between ellipsoid and the geoid, is normally smaller, as we have seen, smaller than the geoidal, the orthometric height, which is the height between the surface of the geoid and the actual ground surface. So we often use this formula, this particular formula, to calculate the orthometric height, which is the elevation, when we know ellipsoidal height and the geoidal height. Okay, I'm not a surveyor, so I'm going to stop at that. And all you need to do is that all you need to know when you're using GIS is that when you're measuring the elevation, the settings that you put in your instrument, you need to consider this calculation, okay? Of course, when you're using a GPS, the GPS just makes it so simple for you. It just gives you a value. But in the back of your mind, if you want a very precise elevation measurement, let's say your interest is to do surface modeling, okay? Surface terrain modeling. And if your interest is to do things like wetland boundary delineation, whereby you need to generate a topographic wetness index, you need to generate the terrain index. When you're using this kind of data to estimate or do analysis of anything of this kind, you need to know that your GPS has to be well set if you're collecting data, but also if you obtain the data from another source. Check on the description of the data on how these calculations were initially done. What did they consider to be an orthometric height? What did they consider to be a geoidal height? and what did they consider to be an ellipsoidal height? Is it correct or it is having challenges? If it is not, then you can manually generate this. Within the GIS software, there are tools that you can use for manipulating the terrain of the images you have. Both in QGIS and in ArcGIS, there are actually tons of the tools that you can use. Now, for those who are using drones, if you're using a drone to capture an image, one of the outputs is the terrain model of the image that you can generate from the drone images. Now, you don't just use it per se the way it is. You need to manipulate it further using this kind of calculation for it to be correct to be used. Okay, and this is one of the challenges we are having in our African continent, is that we think we are doing GIS. We think we are practicing GIS in our organizations, but we tend to eliminate these small minor issues, these small minor calculations in our analysis. We think that the instrument that we are using to capture information is already calibrated. It's not. It's probably calibrated for those other countries, very well calibrated for those countries where they are being manufactured. But when you bring it to Africa, the terrain in Africa is very different. The spatial coordinate systems in Africa that we are going to look at right now at length is very different. Okay, so you need to calibrate your instrument. That's when your data can be useful for project ABCD. Okay, we have had a lot of data that we have collected for our countries, and then when the partners come to use our data, they don't have confidence over it. First of all, we don't even document our data. You go to the field, you collect GPS points, you make a shapefile, and then you distribute it to other people. You've not documented when this data was collected. You've not documented which kind of GPS or which kind of instrument you've used for collecting the data. You've not documented how was the environmental conditions at that time. Okay, so we just use the data per se, and then later we realize that, for example, we get challenges for our officers who do prediction of, let's say, the weather system, or they do prediction of how the disasters are going to happen, the floods. Okay, and the reason is because when you have garbage in, you'll get garbage out. You will not get accurate measurements. And the reason is because, I am sorry to say, we tend to be very lazy in trying to go further to investigate the data that we have. I know we have a challenge of having data, because by the time you get some data, for you feel like it's a breakthrough, because you don't have a lot of data to play around with. But go ahead and check the accuracy, precision of this data before you use it. It's better to use it when you know there are gaps. Okay, there's something that is not good or programmed about this data, but I'll still use it anyway because I don't have any other option. But let that come out. Tell us that, you know what, the accuracy of my analysis is a plus and a -3, or a plus and a -10, because of the quality of the data that you had, so that people can use your data when they know that there are a small gap in this. So even though I'm predicting rainfall to be there tomorrow, there's a high chance that it may not rain. Okay, so that you give that gap in between and say, my prediction is accurate by a plus or -4 or 5, something like that. Okay, I thought I should talk about that. I'm passionate about accuracy. Humphrey, go ahead. Humphrey Kato, go ahead. Your hands are up. Oh, you're testing the system. Okay, let's proceed. Ambrose, Kato, Humphrey seem to be in a different mood. All right, let's continue. Now we have looked at a geoid. Let's go and look at a datum. What is a datum? Jen, I don't know whether Jen
Thank you,
should go
Doctor.
first. Yes, please.
Okay,
Just call me Thomas. You're going to
oh,
make me have a pressure to do a PhD. Okay.
You must
All right.
do. Okay, thank you. Thank you.
Okay.
You have mentioned about describing the tool you are using. Is it a tool? If I may say a GPS, is it a tool?
Yes.
So when you get it, do we have, when you're calibrating it as you want to go to the field, are there these options of joid and you say they are joid, ellipsoid. So which is easier? What do you find there?
So of course, sometimes when we get the GPSs, when the procurement people are doing their procurement things, because we don't have a lot of knowledge, background knowledge, we just order for the GPS and they bring them. Yeah. Now, people who do procurement are not technical people, they are business people. Now, the reason for this training is that you need to know that there are specifications that the GPS must have. Okay. One, the clear one is, at what accuracy can my GPS measure? Most of the GPS that we have are up to 3 meters. But then, if it is up to 1 meter, is it better? For surveyors, they know the accuracy will be very, very low for surveyors, okay? Because for them, they know the level of accuracy their data should be. And if a GPS is 3 meters in accuracy level, it means the measurement is displaced by 3 meters. So if you do precision test, if you do a precision test, what I mean is you go to one location, you take a GPS point for it. You'll have maybe 10.6 meters. Again, you come back after maybe 10 minutes in the same spot. You stand there, you again measure, you'll probably see you get 6.3. Again, you come back, you'll probably get about 6.9. Okay. Now, of course, if your GPS has a good level of accuracy, it will be a little more expensive than a GPS which is having an accuracy of 3. So to Jen, to tell you, our GPSs have all those capabilities, but others may not give you an opportunity to modify. I am going to tell you, for example, the equipment that are used by surveyors. For example, you have your plot of land. A surveyor comes with the GPS or their measuring equipment that is accurate to a level of 3 meters. Just imagine if you lose your plot by 3 meter dimension, how big is that? That is so big. So that's why the equipment that are used by surveyors are up to centimeters accurate. Like the accuracy level is up to about a centimeter, and probably even less than that for some. So that in case they do your measurement for your land, you probably lose only a centimeter if you're losing, or you gain a centimeter. Of course, gaining is better than losing. So you'd prefer gaining than losing. But in case you're losing, you're going to lose a centimeter inch of your data. So the GPSs have these settings that you need to check. Most people only worry about the coordinate systems, which we are going to talk about in details later. But also issues to do with the datum settings, the geoid values, the ellipsoid heights, and all that can be set for some GPS, and then for some, they are automated. They already come with all those settings without you, without giving you an opportunity to modify them. But all in all, what you need to know is that this information has to be checked. You need to check with your GPS to see whether it has ability to modify those kinds of information. If they don't, they will be already pre-configured, and then you will just have to take it the way it is. But of course, you know that the accuracy will not be so perfect. But Jen, also, lastly, it's not that everything must be accurate in the GIS. Like, if you're interested is just to measure where the households are, or your interest is to just measure where the tree species is, a 3-meter accuracy is good enough, because you don't want to do something too precise. It doesn't add any value. When you're measuring a plot of land, then there it becomes necessary to have a very accurate measuring tool.
Thomas, why
Okay.
I'm asking that,
Yeah.
Thomas.
Yes.
Why I'm asking that is that I was working for a project, and we collected data for some specific features, especially where we were implementing that project. But when it was taken back to Ireland, the Dublin, they noted that our GPS coordinates were in Rwanda and Congo. So I was wondering, maybe the GPS was not calibrated or something, but it confused us. We said, this is the real data we picked. How can it be in Congo and Rwanda? So that is the question. Yeah, thank you.
Okay, I'm going to answer that question in the next presentation. And you're going to, from today, you're going to understand it very well. All right.
Okay, doctor.
Yeah. So, Kato, Humphrey? Humphrey, we can't hear you if you're talking. So Peter Hongo, I see your question. Is it a question? Let me answer as I wait for Kato to come through. Peter Hongo is saying, when a certain record number is to be retrieved from a GIS file or aerial census data, kindly explain the number of probes that can be done. Do I understand this question? Okay, Kato, I'm going to respond to you. I see your question in the chat. When a certain record number is to be retrieved from a GIS file of aerial census data, kindly explain the number of problems that can be done. Aerial census data. Peter Hongo, kindly explain this a little bit. Yeah.
Good morning.
Morning.
Yes, I just wanted to know that because earlier you explained the relationship between the data sets. And I wanted a situation whereby we have many data sets from aerial sensors. and we want to know, to search for a certain record from these data sets. Maybe.
Okay. Okay. I get what you're trying to say. So if you want to search for the record in your data from, let's say, your database, first of all, you need, and that's why the documentation of the data is very important. You need to know the column or the field names of the data, number one. So if you know, then you can do a search based on that field. That is one way of doing it. We're going to look at geoprocessing and spatial analysis tomorrow so that we get to understand how you can do a filter, you can do a search by either the attributes, field names, or you can search by location. Now, how do you do a search by location? You can search by location by first defining which area you want to get information about. Let's say it is a hospital. So you first say, okay, where is hospital Nyamwamba? So when you get to know that, okay, hospital Nyamwamba is here. So let me get all the information that is 10 meters from Nyamwamba Hospital. So you start by knowing the location of an area or defining the location of an area. Then you search for information or records that are maybe around it or that are within it. Remember, we looked at spatial relationship yesterday. It could be covered by it, next to it, and all those kind of questions that you can ask or you can use for searching for that kind of information. Thomas, for the presentation, my question is ellipsoidal height, the one taken as elevation. I think I had a problem with audio. Humphrey, kindly let me know because I explained this twice. I don't know if you picked the response that I gave. Okay. All right. This is nice. People are answering questions for my sister Jen a little bit here. So that's good. But I'm going to describe it more in details later. Okay, datums. All right. So my colleague says we need to have a break. You know, when I'm teaching, I completely forget. So please, kindly, let's go for a 10 minutes break. For those who want to take some coffee, for those who want to maybe grab a snack or something, please feel free to do that. I probably need also to take a cup of water. And then we continue. So it will be a 10 minutes break. So Juliet, can you guide me when we shall be able to have this break and when shall we stop? Come back.
I think we come back 11:20.
Okay, 11:20 should be perfect for us to come back from our commercial break. And then we shall be able to dive in and finish the remaining slides for today. Thank you.
Hello, Thomas.
Yes, Fithi. Fitihi Hagos.
You're right. Yeah, from the Eritrean.
Yeah, Eritrean team.
Yes, we are 5 people. We are following in one computers due to the lack of the internet connections.
Yeah, yeah.
Yeah, I see your presentation is very nice.
How many are you
But
today?
I want,
Last time you would be many.
yeah. But I want to ask you, Thomas, for the object data models, as you presented on the objects, the basin, sub-basin, streamnet stations, you make their own tables, and also with relations. Do you hear me?
Yes, I can hear you.
Okay. Can you possible to make this is one to one relation? Is it possible to make one to many relations?
Okay, we'll talk more about the databases tomorrow. But why we are interested
Okay.
in a many to one, okay? For you want a one to many. It is possible to do a one to many. For
Because
example,
as you explained it on encapsulations for the data.
for raster data,
Yeah.
yes, the one-to-one, remember, would make the table or the attribute table to be very large, okay? Because that means each cell
Yes.
has its own record. So that would make it too large. So that's why a many to one makes sure that many cells are related to one attribute table. But there is also where you can have a one to many, okay? There's also a possibility of having a one to many. It means, and this can be implemented very well in objected data model. For example, you can have many trees that have, you can have one tree having many records. And for example, that's what I mean is you have a tree that has a record that is talking about its age.
Yes.
The same tree, you have a record that is talking about its height. You have a same tree
Yes.
that is having a record that is talking about maybe its species, the type of the species it has. So there is where
Yeah.
you're having a one to many relationship.
Yeah.
So
Okay.
it is
It's clear.
possible to, yes, it's possible to do that.
Okay. And also my
I'll
second
explain.
question is for the, okay. My second question.
It's okay. Yes.
For yesterday presentation, how do you measure the depth of the lakes and also the height of the trees in GIS?
Yes. So when I just explained that concept here, okay?
Yeah.
So you
Yeah.
can measure the height of the lake by first of all knowing the
Yeah,
height.
I understand. For measure of the lake is possible to understand. The depth of the lakes. How do you measure?
The
Because
depth,
it is
yes, the depth.
yes.
Yes, that's what I'm trying to explain. So to measure the depth of the lake, you first of all need to know the ellipsoid. Ellipsoid is the measurement at sea level, okay? So you first need to know, so I'm just going to draw here. So let's say you have something like this. Now, measurement at sea level is the ellipsoid. So ellipsoid could be going like this. Okay. Now,
It means sea level.
this is ellipsoid.
Yeah.
The one in red. And then the one in green is a geoid. This geoid here.
Yes. Okay.
So now, if you know the measurement of the geoid, so this would be a lake. Okay. This would be a lake. So all you need to know is the measurement of the geoid just based on these equations. Yes. And then the measurement of ellipsoid, and then the distance between a geoid surface, an ellipsoid, would be the height of the lake, just like I've demonstrated here. So it is very possible to know the height of the lake. So what you need is what we call the surface terrain model data. It's a raster data, okay? It looks like elevation, but it's the
Yes, exactly.
surface, yes, surface terrain model data. And then you'll need to have the information about ellipsoid. Ellipsoid is the height at sea level. So you can be able to know the height at sea level of a certain place from the geoid, okay? So the moment you know those two, then you can just make a subtraction between ellipsoid and the geoid value. So like I mentioned here, I didn't show you. So here, where is the statement? Just different. Aha, here. So you'll be able to see that a geoid model is taken based on the global satellite data, and it can be downloaded as what we call a geoid grids. Okay. All right.
Okay.
So you can obtain a surface terrain model from the digital elevation, from DEM, DEM, digital elevation model. And then you can also obtain a geoid grid, which will give you the height of a geoid at that point. So those two data sets can be able to help you estimate, I'm not saying accurately, but estimate the height of or the depth of the lake.
Okay.
So within the GIS software,
using the formulas, you can calculate the depth of the lakes.
The lake, yes, you can calculate the depth of the lake. But now in the GIS software, for example, in the ArcGIS software, you can be able to use this tool called HEC-GeoRAS. It's called HEC-GeoRAS. So the spelling is,
tool on GIS?
Yes, it's a tool on ArcGIS. HEC-GeoRAS.
Okay.
Okay. And then in the QGIS, there's a plugin called River. There's a plugin called River. It's the one that you can use for doing this kind of hydrological analysis, measurement. You can even obtain the cross-sectional area of maybe a stream or a river or a lake, and also be able to obtain its height. So those two tools, this one is for ArcGIS. Okay.
Okay.
Yes, ArcGIS.
Yeah, this
and
is
then
HEC-GeoRAS.
HEC-GeoRAS.
HEC-GeoRAS. This is for
Yes.
the depth of the lakes to measure.
No, it's a full pledge. They have many tools, but using it, you can be able to calculate the depth of the river, of the lake, and so forth.
Okay.
Of course, the two data sets that you'll use will be the digital elevation model and the geoid grids. Okay, Agos?
Okay, Thomas.
All right.
Okay.
So look
Thank
up
you so
for
much.
yes, look up for those two tools. One is for ArcGIS, and then Rivers is for it's a QGIS plugin, which you can download and install in your QGIS. Okay.
Okay.
All right.
Okay. Thank
All
you.
right, bye. Let's go for a break. Bye. Okay.
Okay. Okay.
Coding. Now, if a datum includes size, shape of the Earth, orientation, and location of the reference point of origin, when you're looking at a datum, you're not only looking at some definition or an acronym per se. It's a system which is composed of these segments. So there are different or several different types of datums that are used in GIS, and they include the horizontal datums and the vertical datums. So what are horizontal datums? These are datums which are used to define the latitude and the longitude of a point. Okay. Yesterday, when we were looking at different types of models, we noticed that the smallest definition of a feature is a point. What I mean is a point, all the lines that you see originates from joining 2 points. And the polygons that we saw originates by joining many lines to make up a loop that forms a polygon. So the horizontal datum, which are used to define latitudes and longitudes of a point, is a datum that can be used within the GIS. Another type is the vertical datum, which are used to define elevation or the depth of a point relative to the reference level. Now, we have already talked about the 3 different reference levels. Majorly 2 of them are very, very key in GIS. When I talk about reference levels, I'm talking about these lines. The first one is ellipsoid, and then the second one is the geoid. So everything on top of the Earth surface is reference based on a geoid or the geoid and ellipsoid. Okay. Now, when we look at horizontal datums, so horizontal datums, since they look at latitude and longitudes, they only deal with things that are X and Y. Now, the moment you introduce Z, then it converts from being horizontal datum to a vertical datum. So that's what you need to know the difference is. X, Y, and Z, these ones are vertical datums, and then horizontal datums. So if you're doing measurements, if you envisage you're going to the field and you're going to do X and Y measurements only, then it's preferable that you work with the horizontal datums. If you're going to do X, Y, and Z, then it's advisable that you deal with or you set your GPS to use vertical datums. The beauty is that in the number of the common datums that are used, they both can take in X, Y, and Z. And if you decide to use only X and Y, it will also work. If you decide to add a Z, then it will also work. So what are these common datums that we know? One is the WGS, which means World Geodetic System, and it was invented in 1984. This is a global datum that is used in navigation and mapping. Now, this is global in such a way that when you're in the US, you can use it. When you're in African continent, you can use it. When you're in Russia, you can be able to use it. When you're in Australia, Queensland, or whether Greenland and all that, you can use the same datum. In other words, in your gadget, the GPS, the phone, or any measuring device that you're using, including the the surveyor's total station measuring equipment. You can set them into that as your preferred datum. Now, if you're in the US, since they are the developers of these datums, they have their precise one that only works in the US, and it's called North American Datum of 1983. However, you can't use it in Africa. You can only use it when you're in North America, not even the whole of America. You can only use it in those areas only. So you'll see that in most of your GPS, it's either going to tell you to use NAD 83, NAD 80 something, there are a number of NADs, or WGS 84 for, and you should always pick WGS 84 because it's a global datum. We shall also see there are other local datums that can be used, like in Uganda, we have Clark 1988, which you can use as your datum. And I think also in Kenya and a number of places. So feel free to Google and find out the local datums that are useful for your country of interest. So example of this datum, like I mentioned, there are a lot of NADs. You can have NAD 27, NAD 83, NAD 83, which is based on Han, and codes 1996. There is also NAD 83 of 2007. There is also NAD 83 of 2011. So you realize that these people kept improving their, or generating or developing new datums as it's. What you need to know about a datum is that it's based on mathematics based on a mathematics calculation that you do on the earth. And this is really something that is too advanced for this course. So if you want to understand if you're this guru or you're a surveyor, you want to set up maybe reference services that people can subscribe to, and you start making your own money. People, whenever people want to use your reference services, they pay for it and do conversion of their data to make it more precise or improve accuracy using your service. Then please go ahead and read more, and probably even do a course in GNSS and GPS course. I'll show you that in the book that I've shared in the classroom. There's a whole section of that you can study more and understand. Now, the reason for this slide is to show you that irrespective of any datum that you're picking, be mindful that there's a shift in each of them. So in other words, your coordinates will be shifted by a certain value. If you decide to obtain data that was in NAD 27, and then you decide to use it to change your datum to NAD 83 of 1986, your data is going to be shifted by a value of 36.3 meters. So in other words, the accuracy is going to be poor at a level of 36.3. So that's what you need to bear in your mind, that if you obtain data that is in a different datum and you shift it to a different new datum, then there will be a shift in your data. So you need to take care of that. You need to, first of all, make a decision that, do I really need to convert this datum? If you're going to convert the datum, can you be able to tell the shift that is going to happen, so that you can report this, that the data that was obtained was in this projection or in this datum, and now we have we then transformed it into this datum. So in other words, our data has been shifted from, let's say, a building. A building was oriented rectangularly in a right position, but when you shift, when you transform your datum from one to another, then your building is going to shift by certain meters towards the right or towards the left, clockwise or anti-clockwise in that respect. Now, GIS is different from other information systems because they include coordinates that define the location, the shape, and the extent of a geographic object. We kept talking about coordinates, 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 coordinates. So what are coordinates? A coordinate is a set of two or more numbers that specifies the position of a point, a line, or other geometric figure in relation to some reference system. So remember, there is always a reference system, okay? Let's say you have this number line and this is the reference system. You're going to know the value of this coordinate or the coordinate of this point based on the reference of this place. So for example, you'll say it is moving from 0 up to 3. And then in the northern direction, it's moving from this point up to maybe, let's say, 4. Okay. So in other words, your coordinate, the coordinates here is going to be 3 x, y, 3 and 4. Okay. Now, why is it a 3? Is because it is moving from the reference point, which is 0 up to 3, and from a reference point that is up to 4. That is if you show it in terms of mathematics. But in a normal circumstance, what you're saying is you're using the surfaces that we talked about, ellipsoid and the geoid, to define that reference. You're saying this place is this at this point based on this reference. Okay. All right. I hope you're picking it up. Now, a coordinate is not something very ambiguous. They're just numbers, and they are a set of numbers. But these numbers specify the position of an object. So that is what coordinates are. So for example, you have this area. The Earth is a circle at this point. And then this object here is actually this object, which is big here. Now, for this section in that object, it's having a coordinate, okay? Now, what we are trying to explain here, that even though it has a coordinate, depending on the datum that you're choosing, the coordinates will vary, okay? So for example, if you decide to use NAD 83, which is the datum of 2007, this year is basically when the mathematicians came up with that particular datum. The coordinates will be 4454, rather 5725 dot, rather 23.23074, and that. Now, compare this coordinate, okay, which is a lat and long, with the one that is in NAD 83 of 1996. So you'll see that these numbers are been shifted from 74 to 47. So there's a big shift between these two values just because you decided to change the position of a coordinate. This might look small in normal circumstance, but when you plot this on the ground, you'll actually see that the shift is very, very big, because this is a shift in the latitude direction, and in the longitude direction, it has shifted by over 0.1 something, because it's shifting from 28 to 27. So this is a very big shift in the value. Now, there's something that is being introduced here. Here, you're seeing values in terms of the latitude and in terms of the longitude. Now, when people are talking about coordinates, sometimes they say X and Y. Yeah. Then you find others are saying latitudes and longitudes. So what is the difference? Why are you saying X and Y? So does it mean X and Y, lat and long, are the same? Absolutely no, it's not. So, and we're going to dwell much on why some coordinates are called latitudes and longitudes, and why others are called X and Y, and why others are called eastings and northings. Okay, so what is the difference between the three names? I would call them names that are being given to the coordinates that we have. So a coordinate makes up a coordinate system. So what is a coordinate system? Just like a system of your body, you have the digestive system. The digestive system has, if I remember, of my high school, you have the mouth, the esophagus, then you have the stomach, you have the intestines, you have the liver. So those are components of a system. So a system is composed of the small nitty parts of it. A coordinate system, just like a GIS system, is also composed of the small nitty gritty parts of it. So it's not just something that is as a whole. There are parts that combine together to make that system. So in a GIS, a coordinate system is a framework. Now, people who have studied too much, they like talking about frameworks. And sometimes you might start thinking maybe a framework is something that is touchable or untouchable. It's matter, it's made of matter, or it's not matter. But what is a framework? A framework is a set of procedures, okay? It's just a set of procedures that try to indicate step by step what something is or should be. So in terms of the GIS, a coordinate system is a framework, so a set of procedures that is used to specify the location of a geographic feature in a GIS. Okay? So don't think the geographic system is very different from the coordinates. Coordinates are actually part of the geographic coordinate system. A datum is actually part of a geographic coordinate system. So those are the nitty-gritties that combines to make a coordinate system. Now, all that we were talking about, the datum, the geoid, the ellipsoid, they're just mathematical formulas. They are not, they're just mathematical formulas. So what makes a coordinate system the way it is because it is a mathematical model that defines a set of rules. I told you set of rules are frameworks, yeah? are rules for representing a spatial position and a distance in both 2 and 3 dimensional space. I've explained when we talk about 2 dimension, we are looking at a flat area. In other words, our coordinates will be X and Y. When we're looking at a 3-dimensional area, something is no longer flat. It is having the X, Y, and the Z component attached to it. And we shall see that when you are looking at the Earth as round or as an ellipsoid, then that is 3-dimension. When you're looking at the Earth as a flat object in your computer, let's say a map layout of maybe administrative boundaries in your GIS software, then you're looking at a 2-dimensional orientation of the Earth. Okay. Now, in the GIS, there are 2 main types of coordinate systems, and that is what should be very important to you. The geographic coordinate system and the projected coordinate systems. So those are the key 2 main types of coordinate systems. Now, a geographic coordinate system, which is a GCS, uses 3-dimensional model of the Earth. Now, we talked about 2-dimension and 3-dimension. So in other words, if you're looking at the Earth as a round object, remember round is not a perfect circle like we mentioned earlier. If you're looking at it as a round object, then it becomes a 3-dimensional model of the Earth. Okay? And in this case, you'll have to do X, Y, and Z. You can do those measurements when the Earth is 3-dimensional. And as usual, it's used to define position of a point on the Earth, just like the same statement we saw up there. Now, what is very important about it is that it uses the latitude, longitude, and elevation. Mark the difference. When you're using a GCS, which is a geographic coordinate system, the coordinates you're talking about, they will be calling them latitude, longitude, and elevation. Okay? Now, what is a PCS? So a projected coordinate system is one type of the coordinate system that is being used. And for it, it looks at a 2-dimensional model of the Earth. It is not 3. So when you're dealing with projected coordinate systems, then just know you're looking at the Earth as a flat object, not as a round object. Okay? So it's based on the projection of what was initially round to a flat area, such as a map. Okay? So, have you ever made a map with the Earth that is round? I don't think so. If you've ever done one, please raise up your hand and tell us that, yeah, I developed a map which was round. Okay? I don't think so. Most of the maps that we see are flat. Okay? So it means they are based on projected coordinate systems. So there are many different types of coordinate systems used in GIS. Now, we are not now talking about the types, but now we are narrowing down to examples of what examples of a GCS and a PCS. Okay? So others are global coordinate systems, like I've just mentioned earlier, the WGS 84, and others can be local in terms of context. What I mean by local and global is that for Uganda, it might have its own local coordinate system, and then Rwanda also is having its own coordinate system. When I was in Rwanda a few months ago, the time shifts. People wake up at normal at 9. In Uganda, that would be too late, okay? Because the time shifts. So also for them, they have a different coordinate system. Also, and we have seen also the US people also have their own coordinate system, including in Europe and so forth. So you can have a global one, which can be used by any country at any one place, at any one point. And then you'll have a local one, which can only be used for a particular region or a country. So you can't use a local one to, for example, you can't use a local coordinate system for Uganda to do mapping for a place in Nigeria. It won't work. There will be a very big shift in your coordinates, as we saw earlier. So the choice of this system depends on the purpose of the GIS analysis and the accuracy that is required. So to work with spatial data in the GIS software, it is important to ensure that all the data layers that are using are in the same coordinate system. So if one layer is not, then you need to do what we call reprojecting. And we are going to learn what is now called projecting the coordinate system from one type to another. This can be done by projecting the data from one coordinate system to another using a specialized tool in the GIS software. So whether you are interested in using QGIS, which is open source, or you want to use ArcGIS softwares, could be Desktop, Pro, or ArcGIS Online, and all the families of ArcGIS, then you need to know that the tools are there which can help you do the projection of coordinate system or a coordinate from one coordinate system to another coordinate system. Let's start with geographic coordinate system, just diving a little bit more. So the coordinate system that is most commonly used to define location on a three-dimensional Earth, and it's based on the spheroid. Spheroid is a round model of the Earth, just like what we are seeing in some of these images. Now, to go further, it's based on the latitudes and the longitudes. I've already described that. Now, to go further, you'll see that east-west scale, and we're going to look at more in scale later, but the east to west scale, called the latitude, rather the longitude range, ranges from plus 180 degrees to negative 180. So in other words, if you want to move from the east to west, you're going to go from plus to minus 180. If you want to move, or if you're moving from the north to south, then you're moving from plus 90 all the way to minus 90 in terms of the scale that you're using. Okay. Now, looking at this orientation or the global part of the Earth, you'll see that the lines that are moving horizontally are the latitudes. And the ones that are moving from up to down are longitudes, just like you're seeing here. Okay. And we have said anything that is moving from up to down moves from plus 90 to minus 90. Anything that is moving from east to west is plus 180 to minus 180. Okay. Okay. So to continue, now you've understood what are longitudes and what are latitudes and what direction do they move from one point to the other. But also you can say, okay, can I try to understand the latitudes and longitudes if I look at an image from above? So when you look at it from above, this is how you see the longitudes. And when you look at it from the sides, this is how you see the latitudes. Okay. Now, just excuse me for 1 minute or so. Okay, so now that you've understood how the latitudes and the longitude look from above and from the sides, this is just trying to help you comprehend and understand what are the latitudes and what are the longitudes. So the longitudes are the ones that run from the north to the south, and then the latitudes run from the east to the west, not from the west to the east. Okay, so you need to know the difference. Okay, so if you say the other way around, then you'll confuse yourself. So it runs from the east to the west. Most people are used to it running from the west to the east. So you'll see from this model that there are two key lines of reference. One is the prime meridian, which runs from the north to the south, and then the equator, which runs from the east to the west. So each of it, when you're trying to measure the coordinates will be in terms of angles. And that's why the values for, if you look at latitudes and longitude coordinate values, they are in degrees. It could be degrees, minutes, seconds. It could just be degrees, minutes, or it could also be decimal degrees. So those are some of the coordinates that are in geographic coordinate system. So the values for the coordinates that are in geographic coordinate system include 1, decimal degrees, 2, degrees, minutes, and seconds, 3, degrees, minutes. So those are the 3 coordinate values that you'll always hear around. And the moment you hear them, just know they are based on the geographic coordinate system. And if they're based on geographic coordinate system, then they're considering the Earth as a round object. So next is we want to see furthermore that geographic coordinate system, as I've already mentioned, talks about all that. What about projected coordinate system? It also uses the X and Y coordinates to represent position on a flat surface. Okay. Now, the main difference between the GCS and the PCS is that a GCS is based on the three-dimensional model of the Earth, while the PCS is a two-dimensional representation of the Earth's surface. This means that a GCS can accurately represent the Earth's curved surface in a three-dimension, while a PCS can only provide an accurate representation of the Earth's surface in a two-dimensional model. In GIS, it is important to choose appropriate coordinate system for a given analysis or a map. So a GCS, which is a geographic coordinate system, is typically used for working with data that require a high level of accuracy and precision, such as surveying or global navigation system. So for them, they are always relying on a geographic coordinate system. However, for the PCS, it's typically used when working with data that will be displayed on a map. So the moment you know that your interest is to generate data that is going to be used for making a map, then it's better that you use the projected coordinate system as your coordinate system measurement. Okay. And I'm going to tell you the reason why you decide to use that coordinate system, because when you're using a geographic coordinate system, there is a high level of distortion in the measurements that you have. These measurements include the area, the distance, and so forth. Now, before you use a projected coordinate system, you need to project the Earth from its round shape, which is ellipsoid, to a flat shape, which is normally called a map. And that's why normally there's a term called map projection, because you're moving from a round Earth into a flat surface, which is a map. So what is this process? This process is called projection. It refers to a method and a procedure that is used to transform the spherical three-dimensional Earth into a two-dimensional planar surface. So basically, it is a mathematical means of transferring information from the three-dimensional Earth, okay, surface into a two-dimensional Earth. So there are many different map projections also that are used, and each with its own advantages and disadvantages. Some projections are designed to preserve certain properties of the Earth's surface, such as the shape, area, distance, and length, while sacrificing others. And we are going to see that in details as we move along. So the projected coordinate systems are also referred to as map projection. So when you hear people talking about map projection, which map projection did you use? Which map projection did you use? They are referring to the system which is projected coordinate system. So to choose an appropriate map projection for GIS project, it's important to consider the purpose of the map and the location, scale, and the data that is being used. So for example, a projection that preserves distance might be appropriate for calculating the travel time between locations. So for example, if you're developing a service, you're developing a map that will measure distance from one place to the other, then you need to use a map projection that preserves distance. Remember, when you're converting the Earth from its round shape to its flat shape, there's a lot of distortion that happens. And we're going to, at some point, probably, if possible, watch a video that talks about these projections in details. And while a projection that preserves area might be appropriate for mapping a land use or a population density. So all we're saying here is that it's important that you make a right choice of which map projection you should use, because each of them can be accurate for one measurement and not for the other. So you need to have that sacrifice within you and say, okay, because I'm doing ABCD, let me go with this, and then sacrifice the aspect of the area. So if you want to measure distance, you sacrifice the accurate measurement of the area. However, all map projection representing the Earth's surface as a flat map creates distortion in some aspects of distance, area, shape, and direction. I've already talked about that earlier. Now, the types of map projection. One, there are majorly three types. One is called conical projection here. Another is cylindrical projection. And then the last one is planar or azimuthal projection. Now, what we have been talking about every time I'm talking about map projection is whereby you're having a round Earth that we know is round, and then you're converting it into something that is flat. So you can either follow this trend and say, for me to obtain a flat area, let me go from round to conical to flat. That is one option. The other option is to go from round through cylindrical to flat. And then the third option is to go through a round Earth through planar projection to obtain a flat area. Now, what are the advantages and the disadvantages? So a cylindrical map projection, how it works is more like you put a wire mesh on the round Earth, you shine a light in the middle, and then it will create sort of the lines. It will draw the Earth features on the cylinder, but this cylinder has a mesh. So in other words, you'll be able to see this mesh or the lines or the mesh of wires, let's say, represented, and then the geographic map or boundary drawn on it. So when you cut this cylinder from one side, like say, let me cut it from here up to here, and then I open it, okay? And then I open it and make it flat. This is how it would look, okay? It would look like something like that. So that is for cylindrical map projection. And for sure, we are going to watch a video that explains the different map projections so that you can understand them in details. The second part is the conical map projection. The conical map projection, I think I have two teachers. Some people are also drawing. I'm also drawing. So, okay. So the second one is the conical map projection. What is a conical map projection? So just like a conical name is, it's a conic, so it's based on a conic object or a cone, okay? This is one way of portraying the Earth. However, they are severely distorted at the poles. So for example, the poles are these areas, the northern pole and the southern pole, okay? So if you're interested in mapping areas from the north up to equator, then you put this cone on the top part. If you're interested in doing the south part of the hemisphere, then this cone is placed on the bottom section. Okay, so depending on what you want to map. But at the end of the day, when I cut this cone and open it, this is what I'm going to see. Of course, as you can see, the cone has the sharp part, but the earth is just stopping around here. So the cone won't be having the tip, but it will just have only this section. Okay, so when I cut it and open it, this is how it's going to look at the end of the day. But as you can see, Africa no longer looks like Africa. North America doesn't look like North America. And the Russia as well as the Australia is looking even more weird. Okay. If you compare that with the cylindrical, things look to be a little normal. But as you can see, the Greenland is almost the size of Africa. Yet it is not true. Greenland is a very small area. So what we are trying to say is that every projection that you select distorts the map. Distorts the map in terms of area, in terms of the length or the distance of, and in terms of the shape of an object. So these are the benefits, okay? One, parallels appear as arcs with the pole and meridians at a straight line that converge to the same point. We have seen that all these lines are more or less converging to the same point. It represents only one hemisphere at a time, north or south. I've just explained that if you're interested in the northern hemisphere, the northern hemisphere starts from the northern pole up to equator, and then the southern hemisphere starts from the equator to the southern pole. So if you decide that, okay, I want to do the southern hemisphere, then instead of putting this cone on top, then you put it this time on the bottom, okay? Now, moving forward, so it's suitable for representing middle latitudes. So if your interest is to map any area, Europe, North America, and all that, you may not be able to achieve a good accuracy. If your interest is also to map areas that are within equator, it's also not suitable. It is only suitable for areas in the middle latitudes. The middle latitudes can be in the northern hemisphere, or it can be in the southern hemisphere if you want to. But areas that are lower down here and around equator or on the northern hemisphere are not suitable for mapping when you're going to use the conic map projection. Okay. So the disclaimer here is that although the conic map projections are best suited for use as regional or hemispheric maps, the latitudes, as I mentioned, they rarely complete the world map. So most of the world maps that you've seen are not in a conic map projection. Very few are there like that. Okay. Next is the planar or the azimuthal map projection, and it can be visualized as a flat sheet of paper tangent to any point on the globe. So this is a flat sheet of paper. You can put it on the northern hemisphere, you can put it on the sides, you can put it at equator, depending on how you want it to be. So right now it's in the northern hemisphere. I could also put it in the southern hemisphere like that. I could also put it on this section and say, let it be there. I could also bring it on this other end and put it there. All that is important is that it has to be tangent. The direction that you're putting has to be tangent to the surface of the earth, either of any direction that you want it to be. Now, it is suitable for showing polar regions. So areas that are in the polar region are well mapped using the azimuthal or the planar map projection. There are, however, 3 types of them. So there is equatorial, zenithal, or azimuthal projection. So equatorial azimuthal projection is the part A, which means that you're putting the flat object at the equator. If you decide to put it at the lower altitudes or any part which is not equator or the poles, then it becomes the oblique zenithal. If you decide to put it on the poles, either in the northern pole or in the southern pole, then it becomes the planar zenithal. So for map projections, there are 3 types. One is the cylindrical, conical, and planar or azimuthal. So within each of it, there are still more types. So for example, for cylindrical, there are more types of cylindrical map projections. For the planar, there is equatorial, oblique, and polar zenithal. Okay. Any question up to this point? Okay, so let's just watch a video quickly, and then we shall be able to come back to
Yeah, Thomas, as you load the video, I have a question. Hello, Thomas.
Sorry, yes, I can hear you. Please go ahead.
Yes, I have a question. You said if you want to get your products as maps, that you should use the projected data, right?
Yeah.
Coordinate system, but these maps have elevations within them as you're interpreting them. So if you're using projected data and you are missing out on the Z, the X, Y, Z, will the maps still come out as if you use the geographic coordinate system?
Yes, so basically what you're doing is for geographic coordinate system, when you do a conversion, it becomes a latitude, okay? Rather the altitude, it becomes an altitude, which is the height above the sea level. Okay, is that clear?
So, because I thought it, okay, now I thought X is the axis,
Guys, what's crack?
the X axis, okay. So it is now that it misses out the Z, the Y becomes the altitude.
No, yes, the Y becomes, not that the Y becomes the altitude. There's just, I'm going to explain it in details. What we are saying is, and Jen, you need to get this. We are not saying that you can't measure elevation in a projected coordinate system. What we are only saying is that for you to establish a better accurate representation of the elevation, then you need to work with data in a geographic coordinate system. But if you're working with it in a projected coordinate system, bear in mind that the best way of doing it would have been the other way around. Of course, the softwares are very smart these days. They will allow you project your data from geographic coordinate system to projected coordinate system. And then they will manipulate. There is where they ask you to define what we call what was it? They allow you to to enter what we call the XY tolerance. Okay, so you need to specify the tolerance. So the tolerance is what we normally call the conversion factor. So the software will
Okay.
ask you that, oh, you're converting from this point to this point. What is the tolerance? What is the conversion factor that you want me to put for the case of, for example, the elevation? Because I'm converting my data from geographic coordinate system to projected coordinate system. It means my elevation data is going to be converted to altitude, but at what factor can I use to, people have generated those mathematical things and they've come up with the right conversion factors that can be used. For example, if you're converting your data from that is, you're converting it to universal transverse Mercator, which I have not talked much about, which people normally call UTM. If you're converting it from that to UTM, which is UTM is a projected coordinate system. So if you're converting it to that, then you need to know that the conversion factor, UTM, first of all, is measured in meters. And then you'll have the geographic coordinate system is measured in degrees. So how do you convert, even if I type in Google right now, degrees to meters, there is a conversion factor that can be given to you. So you need to enter that value very well. So for example, if I go to Google, Google is always our best friend, degrees to meters. Okay. So you'll find that there are so many people who have tried to estimate different measurements. For example, 1 degrees to minutes is about 1 deg to meters. There are people who have come up with ways of how to estimate a degrees versus the meters. So that will be the conversion factor that you will need to insert in your software when you're doing the conversion.
Okay.
Okay,
Thank
John.
Thank you so much.
You're welcome. It's unfortunate that, fortunate that we are doing an introduction or the conceptual theories and principles. So I can't do a lot of practical things to show you how they are supposed to be done. But nonetheless, let's watch the video. I need to share the sound. Yes, my sound is being shared. That's okay.
This is Chris here at Mango, and today I'm bringing you a video on map projections. Now I know what you're thinking, map projections, ooh, this is going to be all about maths and geometry and complicated equations. But don't worry, this is going to be a beginner's guide, so we're going to be gentle with you and we're going to ease you in. Hey guys, what's cracking? This is Chris here at Mango, and today I'm bringing you a video on map projections. Now I know what you're thinking, map projections, ooh, this is going to be all about maths and geometry and complicated equations. But don't worry, this is going to be a beginner's guide, so we're going to be gentle with you and we're going to ease you into the basics of map projections, and hopefully by the end of this video you'll firstly understand what a map projection is, and more importantly, you'll understand what impact it has on your map applications, especially in terms of measurements of distance and area. So what's a map projection? A map projection, as you can see on screen at the moment, is the process of transforming a spherical object into a two-dimensional flat surface. So that usually means taking a sphere, in this case the Earth, and transforming it into a flat square or rectangle. Now, as you can imagine, if I took a football and I began cutting it up with a knife and tried to flatten it out, it wouldn't fit together perfectly into a rectangle or a square. So a projection is a mathematical equation that tells a mapping system how to fill in those gaps and how to populate the entire rectangle. When it comes to map projections, distortions are the name of the game. Think back to our football. If we slice the football up and we try and spread it out into a rectangle, in order to make that shape, we're going to have to introduce some distortions of the picture that was contained on the surface of that sphere. We're either going to lose the distances, they're no longer going to be accurate, or the shapes will be inaccurate, or the areas will be inaccurate, or the directions will be inaccurate. So when creating a projection, it's always a question of compromise. Which of these attributes are we willing to compromise? Some projections try to maintain the correct distances between locations on the surface. Others try to maintain the area or the shape or the direction. And many projections try to find a sweet spot, a balance in all of these variables that gives the most accurate visual representation for a specific area on the globe. That's why you often see projections that are for individual countries, states, or regions. So let's take a look at one of these projections and look at the distortions that it introduces. Today we're going to be looking at the Webb Mercator projection. Now I've chosen the Webb Mercator projection not because it's the best projection by any means, but because it's probably the most viewed projection of all map projections today, because this is the projection that's used by web mapping systems such as Google Maps, Bing, or the base maps that you see on Mango. So the map that you see on screen at the moment is a Webb Mercator projection of the globe. Now, for those of you who are digital immigrants like myself and learn geography from a textbook rather than Google Maps, you'll be looking at this map and you'll notice that there's one or two things wrong. First of all, Antarctica seems to have a larger land mass than the rest of the continents combined. And secondly, Greenland looks to be at least as large as Africa. This is because the Webb Mercator projection creates very large distortions at the poles because it's stretched the sphere out into a square, whilst naturally that sphere wants to be stretched into a rectangle shape. Now, there's a lot of technical reasons why Google, who originally created this, this projection system, chose to do that. Mainly it was to do with storage efficiency and the speed which they could send map tiles across the internet. But I'm not going to bore you with the technical details of that today. Maybe we'll save that for another video. Okay, but the main thing here is these distortions at the pole. So as we see here, Greenland is the same size as Africa. So as the image shows here, the image on the left shows Africa compared to Greenland using the Webb Mercator projection. As we can see, they're nearly the same size. On the right, we see how big they are in comparison in reality. As you can see, Greenland is a fraction of the size of Africa. So now that you understand projections and you also have an understanding of the distortions that they can introduce in your map visualizations, you're probably wondering, what practical impact does that have? What impact does that have on me when I'm interacting with a map application? Or if you're a maker of maps or web maps, what impact does it have for your users? I think one of the best ways to demonstrate this is by using circles and radiuses. So we'll go back here to this base map on Mango that's in the Webb Mercator projection again. And what I'm going to do is I'm going to draw a couple of circles on the map and using a radius tool. So I'm going to draw one circle up here near Greenland, and let's make the circle, say, 500 kilometers wide. Okay, so on this map at the moment, that 500 kilometer wide circle, in terms of my screen size, it's probably about 5 centimeters wide. So let's see what happens if I draw the circle again close to the equator. We can see that now 500 kilometers is smaller than the tip of my little finger. So there's a big difference between what the area of a 500 kilometer circle looks like near the equator and what it looks like near Greenland. So how can that impact your tools and your queries and your measurements? Let's look at a layer that I've prepared on this map previously. So this is a map where I placed 2 points, one in Mexico and one in northern Canada. And once I placed the points, I used a buffering tool to draw a circle exactly 500 kilometers around each of those individual points. So the two circles that you see on screen, the yellow ones, on the surface of the true Earth are exactly the same size, and they have an exact radius of 500 kilometers from that point. But looking on the map, you can't see that. It's obvious to see here that the circle in Mexico looks much smaller on this map and the circle in Canada looks much larger. What's more is the circle in Canada, as you can see, is no longer a perfect circle. It's starting to resemble an egg shape. And we can see that the dot, the green dot here, which is the center point of that circle, looks like it's much closer to the southern edge of the circle than it is to the northern edge. But the reality is that every edge around this circle is exactly 500 kilometers away from the center. It's just the projection that is making the map or making that circle distort and display like an egg shape. It's the projection that's making it look much larger than the circle in Mexico. And before we go, I want to show you one last application that really solidifies the point of how large these distortions are. This is an application that's been built using the geodesic circle plugin for Leaflet, link in the description below. And it allows me to move the cursor around the map, and the circle that you see on screen is exactly 1,000 kilometers. So we can see how small 1,000 kilometers is on this projection when we're near the equator, and we can see how massive the distortion is as we move north towards the poles. And that brings us to the end of this video. If you enjoyed the content, don't forget to hit the like button below. And if you'd like to see more videos,
Okay, so I hope the video has enabled you to have a small background or understanding of what distortion and what map projections are and why we need it, and probably give you a good understanding that there are different types of map projection. But let's dive into what most people probably have done or are interested in doing or will have to do after this training of the GIS and remote sensing is making a map or designing a map. So some people think that when you're a GIS person, your work is to develop maps. Not necessarily. We have seen a lot of details of, and we're going to see a lot of it tomorrow on how you can run analysis, can generate very nice products. But when you generate these products from your computer, let's say you're an expert of a GIS in your organization, it will remain a mystery in your computer. What if you want to share it with other people and you want them to see it? Maybe they don't even have the software in their computer. So the best thing to do is to develop a map and share it with them, but also be able to get it out of your computer to another person's computer who doesn't have the software. So what's a map? A map represents geographic feature. It's all about geography. It's all about geographical features. So don't feel bored, and it's all about spatial data. Okay, so it represents geographic feature or a spatial phenomenon by graphically conveying information about location and attribute. We'll see in different types of maps later that you can convey information from a map, and the information you're conveying is an attribute-based information, okay, but geographically conveyed. So a map portrays three kinds of information about geographic feature. One, the location and extent of the feature identified. Two, the attribute of the feature which describe or characterize that feature. Three is the relationship of the feature to other features, okay? So those are three major, I'm not saying all, major information that is conveyed from a map. or using a map. Now, when you make a map, there are things that are called elements of a map. So one is your map should have a title, whether the title is part of the map or it is written as a caption in a map, in a Word document or in your document. A map must have a title. Two, a map must have a legend. Legend serves as a decoder. I don't know if you know what a decoder is. If you have DSTV at your home, it's trying to convert the information it's receiving from the provider of the DSTV into your TV set. So basically, you're trying to explain what is contained in the map using a legend. So legend is more like we used to call it at some point as a map. I'll remember with time. Another element is the north arrow. The north arrow helps somebody to orient themselves in the map. So when they get your map, let's say in a paper format, they'll first turn it the other way around to make sure that the north arrow is facing the northern part in their mind, definitely. Not that that is the direction of the north at that point, but they'll twist the map to make sure that the north arrow is in the north direction. Yeah. Scale. The scale explains the relationship of the data frame extent to the real world. And we'll look at that in details. Most scales use a ratio method or format. Citation. Some people mostly forget this part of citation, but you need to give credit either to yourself or give credit to somebody who sponsored you to collect this data, or people who contributed this data for you to make that map. Okay, so citation is very, very important. Next is, this is just a map that was designed, and it's showing the different elements that a map should have or may have. There's a media edge and a neat line. So those are optional. You can have a media edge or not. You can have a neat line if you want to or not. But you'll need a title. You'll need the north arrow. You'll need a legend, and you'll need a scale bar. Okay, so the scale bar is the one that shows the scale that has been used in the map. It's either measured in the unit scales that are available out there, or as a ratio of what is in the ground versus what is in the map. So when you make a map and give it to people, there's a high chance that you will not be there to explain what is in the map. You just make a map, it is pinned on the wall. Every day people pass in the corridor, they see that map. You're not there to tell them that, hey, by the way, what you're seeing here is this thing, okay? You just put it there. So the map should be able to communicate to the reader of the map, even when you're not there. So these are some considerations that you must put. And I'll show you some of the tricks that you must do to make sure that the map communicates to the audience or the people visualizing the map without you being there. One is a geographic area of a map should be restricted to the extent of the map subject data. Okay, don't make a very big map and then the content inside are very tiny. It doesn't make sense. The background data element, what I mean is you can include the base maps to support the subject matter of a map, as well as provide orientation. So for example, if you include the streets, the city points of interest, and the boundary, all those things will help somebody know that the information they're looking at in the map is based on a certain area, and they can orient themselves, especially if they know the place. Let's say you've ordered for an Uber, and then it tells you that, okay, this Uber is at this point. In most cases, you'll first zoom in your map, and then you look at the street. The street name alone will tell you that, oh, the Uber person is either very far or very close to me. The names of the places available or any point of interest, it could be a school, it could be a hospital, it could be a market or a supermarket, will be able to tell you that either the Uber person you've ordered is either very far or very near. Symbolization, the choice of the symbols that you use in the map, either make it or break it. So this is in terms of the choice of the color, the line, the width. Sometimes you can put a 2-lane road to be thicker than a panya, or a panya is a Kiswahili word. I'm sorry. I wanted to refer to maybe a path. Okay, so you have a path, and you can differentiate between the path of a map, of a road, and the 2-lane highway using the thickness of the line of those two objects or roads. The label, while it may be tempting to label all features shown on the map, doing so can block underlining features, create a clustered looking map, and create confusion. So make sure that when you're making this map, you take into consideration that the labels that are there are only important labels. Don't label everything in the map. Things that are not supposed to be labeled and can be seen easily. For example, if the lake or a water body is there, you may decide to put a label, or if it is known. For example, in Uganda, I know where the Lake Kyoga is. I know where Lake Victoria is. Do I have to label them? No. Everyone knows that this is Lake Victoria, this is Lake Kyoga. Okay, so I can decide not to label that and label other features. The legends are key, used to decipher the symbol or the symbology of the map. They need to be legible, not very clustered, and easy to understand. Choice of colors and the symbols are very important here. You cannot put the symbol of a mosque to represent a church. It will cause a lot of confusion. You're saying these are locations of different mosques in the city, and then the symbol that you put in the map is for the church. Somebody will just get so confused. They'll be looking for the mosque because the symbol you've used is different. Metadata, all maps should document all sources of the data. And this is very key, especially when you're publishing an online map. Shape files that we download online should have metadata. So metadata basically tries and describes some of that information. I'll show you some of the metadata in some of the online maps within the classroom that you have. Locator map. So an inset map is very, very important. It's used as a locator map. So it helps to include a smaller, it's helpful to include a smaller inset map showing the location of a mapped area. Let's say I'm mapping a small district in Uganda. So I can put the national boundary and then show where that boundary, where that district is. So let's say I have here a map that I'm trying to develop. Okay, I can decide to put an inset map of Uganda. Forgive my drawing, it may not be clear. And then probably I'm working on a district in, let's say, central Uganda of Wakiso. Okay, so I put, this will be an inset map. It will show in Uganda where Wakiso is. And then I can either use an arrow or something like that to show that. So this will be an inset map, and this will be the actual map that I am working on. All right, so an inset map or a locator map, those are all the same things that are represented within the GIS. Tricks or some tips to make a professional map. Before you make the map, if your boss comes and asks you, sir, madam, I want a map for a presentation, ask your boss or your superior, or if you're just making a map to showcase your products, ask yourself, who are the audience of this map? So before designing your map, consider who your audience is and what they will be using the map for. So ask your superior, what do you want the map for? And which people are going to consume the map. So this will help you determine what data to include and how to represent them. Choosing the color of the scheme. So select a color scheme that is easy to read and aesthetically pleasing. Okay, don't just mix red and green. All they are so bright and then it's totally messed up. So make a map and choose colors that are pleasing to the eye, that will attract the reader to appreciate the map that you have. If you don't know about the colors, you rather just make a map black and white to still communicate better information than struggling with the different colors. Be consistent with the styles, okay? If you're making 10 maps for a certain subject, and then you decide to switch colors, for example, you decide to switch symbols. In one map, you're using a rectangle, and another one, you're using a circle, in another one. So that causes a lot of confusion. So be consistent with the style of the maps that you are generating. Simplifying your data. Avoid clustering your map with too much information. I teach in a university, and sometimes students make maps that are very weird. There's some information that are not necessary. They shouldn't really include it in the map, but for some reason, because they use that layer during analysis, they keep it there, and yet it's not making the map to look as nice as it's supposed to be. So simplify your data by using generalization techniques, which I'm going to show you in the next slide, which helps you to smooth the data, aggregate, or simplify the data that you have. Label your data. So label your data clearly and legibly using descriptive labels, which are easy to read and understand. Eunice, I'm going to come to you shortly. Adding a legend. A legend helps to explain, just like I've mentioned, what the different colors, symbols, and labels in your map is representing. This will help your audience understand the data and what you are presenting. Consider the map projection. This is also very key, that choose an appropriate map projection that accurately represents your data. Different projection can distort the size and the shape of the geographic feature. In the YouTube video that we have watched, depending on the map projection you're having, if your interest is to communicate a different information or attract the attention of the users, then you can decide to use a projection that distorts your map according to your interest. But in most cases, this is not our main goal. Our main goal is to communicate precisely the actual and accurate information in the map. Testing your map. Test your map with a sample audience to ensure it effectively communicates the data you intend to I know for those who are making maps for reports, your work is to just, you want to finalize the map and give it to your superior, okay? But I mean, call a colleague and ask, how does the map look? Is it perfect or it's weird? So ask that and people will give you a response. Eunice, you had put up your hand. Kindly turn on your mic and speak to us. Eunice? Okay. Eunice, if you're still interested in talking to us, feel free to let me know. Okay, I have a lot of questions in the chat. So before I go to map designs, let me respond to a few. Okay, Michael says, yes, you can also add the grids in your map. You can, in the documentation or in the citation, you can show or explain the source of the data and the period when the data was collected. So this is all about metadata. Of course, the borders are very, very important. In the administrative boundaries, you can add those borders. Okay, so Michael, yes, you're very right. All that is important. It's just that I didn't mention them, but they're all important. Okay. Standard convention. So it depends on your organization. It depends on the subject. For example, the colors. If you're making the map and you work for National Forest Authority, you know that the colors are green or something like that. If you're conveying information about natural resources, definitely water, you can't put water to be red. It doesn't make sense. Water is always blue. You can't put the forest or vegetated areas to have maybe black. It won't convey. Vegetation is always green. So those are normal life colors or experiences or choices that you will have to make, because you'll ask yourself, okay, if somebody sees a black forest, will they think it's a forest or they'll think it's just a rock somewhere and not a forest? Okay. All right, Eunice, thank you that I answered your question. All right. Types of maps. I wonder how many maps you've made and if any of them qualifies to be in these types that are available here. One, you can have a feature map. What is a feature map? Feature map is used to map points, lines, areas, and provide nominal information. Nominal means numbers, okay? So no attempt is made for the symbols to represent true scale. So basically what you're just saying is that you can decide to make your dots to be bigger, and you're not interested in saying this dot is different from this one. The dots are all the same, but in normal sense, these dots might be different. For example, each dot, if it is representing the retail shop, it might be some retail shops are bigger than others. So you'll have, if you are to generate a certain map to show the differences in the features that you're seeing, then you can have this dot maybe smaller than this one, which is representing a bigger retail shop. Also the roads will just be the same size, but yet there are highways, there are major roads, there are smaller roads, and there are others are paths. But in a feature map, all the roads are the same. You don't differentiate the sizes of the road. So those are feature maps. Then we have the chloropleth maps. The chloropleth maps depicts quantitative information for an area. So this time The size of the road will have to be represented based on what is actually there. A highway must be different from a major road or a smaller road. Tarmac road should be clearly differentiated from a non-tarmac road. But in this example, they're just showing population density, for example, persons per square mile or something like that. So a mapped variable such as population density may be represented in a map. So polygons define area boundaries such as counties or census tracts. Each polygon is given a color shading or pattern that is corresponding to the value for a mapped variable. In this case, any area that is dark or black, but really dark black, I don't know whether that color is there in existence, but those are areas that are having population density of above 1,000 per census tract. And then in the middle or between black and gray, there's a gray color here. So this gray is showing any persons that are between 101 to 1,000. Next to it are 50 to 100 and so on. So basically you can represent the different attribute information. In this case, quantitative. It has to be quantitative, not qualitative information, but quantitative information in terms of numbers. Next is another type of the map, which is called the dot density map. It can also be used to represent quantitative information, but in this case, it's based on points. Okay, the earlier one is based on areas or polygons. Now here it's based on points. So what is it saying? It shows quantitative data and dots or other point symbols are plotted to represent the values. Okay, so the quantitative information, 10,000, 100,000, 10 or 20 are all represented in terms of the dots. So dots are placed in a polygon such that the number of dots equals the total value total value for that particular polygon. However, note that the dots are typically placed randomly within the polygon area. So for example, if I have this polygon and then I am trying to represent population density. So I can put these dots here. Okay. And if I put maybe 3 of them only or 4 of them here. So this will mean that this polygon is having high density number of people compared to this. Now, the dots at any one point are randomly placed. Doesn't mean that they have to be the way they are the second time I do the mapping. But what I'm trying to imply here is that this polygon A is highly dense compared to polygon B because it has more number of dots compared to this polygon. Isoplates. Isoplate maps, also known as contour maps, display lines of equal value. So, for example, the contour lines, as the statement is mentioning, every contour line is of a certain elevation, and they're always labeled. So isoplate maps are used to represent contours, continuous surfaces. So if you want to represent or show rainfall in a vector format, you can use isoplate maps, and things like rainfall, elevation, and temperature, which are best represented using a raster data model, can be represented in a vector data model using the isoplates. Okay, so isoplates are more like contours. Okay, note that the isoplates are typically estimated surfaces with the lines drawn based on measurements at a set of point location. So this, what it means is that if I have my area here and I decide to draw the isoplates, and I decide to draw the isoplates. So what this statement is basically saying is that these surfaces, so if this is maybe 5, let me get another color. This is maybe 3, this is 2, this is 5. Okay, so those values are drawn based on measurements at a set of point location. Okay, so it means at this isoplate, which is value 5, is based on a certain point of, let's say, a point of rainfall value at that. So it is just trying to estimate that anything around this area within the range of isoplate 5 is having that value of the rainfall. Okay. Now let's wrap up today by looking at the map density, or rather the map scale. So all maps or digitally displayed data have a scale, and a scale is a relationship between the distance on the map and the corresponding distance projected on the ground or on the earth. So map scale is often reported as a distance conversion, such as inches, miles, meters, kilometers, and all that. Meaning 1 meter on the map equals to 1 kilometer on the ground, okay? Also, they can be expressed in terms of unitless ratios, meaning 1:24,000 indicates a 1 unit distance on a display equaling to 24 units on the Earth's surface. So what I'm saying is, on the Earth, the distance between town A and town B might be 10 kilometers. Okay, I have 2 towns here. In the ground, if I'm to travel or drive my car, I'll have to
that's
travel.
why for me, immediately the next day, I started my
After break, you go home and sleep. But we break.
Okay, so I have town A and town B. On ground, the distance between these towns are 10 kilometers. Now, because in the map, I cannot actually draw them as 10 kilometers apart, because my map, my screen is not even 10 kilometers. It's probably not even a kilometer. So I can't have a map which is 10 kilometers in actual sense. So what I do is I say, on my map, 1 equates to 10 kilometers. Okay. 1 unit 1, it could be, let's say, yeah, in terms of ratios. So it means when somebody goes to my map and they are trying to know the distance between A and B, they can just look for, they will be able to measure if from here up to here is 1, And then from here up to here is the second part of the road. And then this would be a half. In total, they will be able to know that this is one part of the road, second and a half. So 2.5 times 10, 2.5 times 10, because one value 1 is equivalent to 10. So if there is 1, 2.5, that means I have 2.5 times 10, which is going to be 25 kilometers in actual ground. Okay, so that's how people utilize the scale, and that's how the scales are useful in the map. So the notion of large versus small scale is often confused because scales implies a ratio or a fraction. For example, a large ratio signifies a large scale map. So as a 1 to 204, 24,000 scale map is considered large scale relative to a 1 to 100,000 scale map. So most times when I'm teaching my students, I ask them, okay, can you tell me the difference between a large scale map and a small scale map? So here we have the pictures that are showing us the differences. So with a large scale map for Japan, you'll be able to see the whole of Japan, okay? On the other hand, on a small scale map of Japan, you will not be able to see Japan completely. You will actually, it will be a very tiny place here. So this is also Japan. This is Japan in a small scale map. But in a large scale map, you'll be able to see it clearly. You'll be able to see even areas of Shikoku, the pronunciation, Sado, and Honshu. You'll be able to see these particular areas. But in a small scale map, you can't even see any label of the different parts of Hong Kong. Actually, you'll now be seeing the whole, some of the part of Asia instead of just Hong Kong. So what does it mean? In a small scale map, you will see a large area. So now I'm seeing the whole of more like part of Asia, or the whole of Asia, including part of Africa. Compared to a large scale map, I can't see Africa. I can only see Hong Kong or Japan in this case. So for a large scale map, you see a small area, but the benefit is that it's in details. So for large scale, you see a small area, but also you see more details. Okay. In a large scale, a small scale map, you see a large area, so it's opposite. Okay. You see a large area with the less details. Okay. Now we have understood those two parts. For a large scale map, you see a small area, but with more details. For a small scale map, you see a large area, but with less details. Now let's us look at the units of the scale. For a large scale map, the unit here is 250 kilometers. For a small scale map, the unit here is 3,000. Meaning this is the value of the scale is going to be probably more than 10 times, I think over 12 times larger for a small scale map than for a large scale map. So you need to know the difference. So when you see the map, two maps there, if you look at the scale is 250 and the scale is 3000. Even before, you should just know that this is a small scale map because the scale value is bigger than this one. So you need to tell the differences. And the moment you see a scale, a small scale map with a large value, then you should just know that the details that is in there, I cannot tell. But also the benefit it has is that you're seeing a bigger area of that area of interest than when you're using a large scale map. So ask yourself, when you're going to do mapping for your country, do you decide to use a small scale map or a large scale map? Which one is better? So you need to look at that as you're making that decision. Lastly, we are going to look at generalization and what it is. Just left with should be 1 or 2 slides, and then we close up for today. So generalization is a process of reducing the level of details or complexities of a map. However, you retain the essential information that a map has. You're doing a little bit of reduction or exaggeration on the symbols that you're using in the map, but you're not losing the information that you have there. So the goal of this is to create a map that is easier to read and understand, but while still conveying the necessary information. Map generalization techniques can be applied to various types of maps, like the examples I've mentioned up there. So for example, we also have others called topographic map, thematic map, navigation maps, and so forth. The level of generalization here will depend on the purpose of the map, the scale, and the intended audience, like I mentioned. We have understood what a scale is and how it affects the map. We have talked about the importance of intended audience, and we have dwelled also a little bit on the purpose of the map. What is the map going to be used for? So here, for example, a topographic map may be used to show more details than a road map. And a map intended to experts may require more details than the map intended for the general public. So some common techniques may include simplification, displacement, and exaggeration. Now, going further, you'll be able to see some of the processes or the techniques that are used to generalize a map. For example, you can fuse a map. So this is the actual map before doing any generalization. So when I do a fuse, what I'm going to do is all these small, tiny parcels will become a single polygon. If I want to do the simplification, I'll make sure that these curves are no longer there, and then I just make a whole polygon without meandering, too much meandering, so that I have something like this. When I decide to displace, I push this road away, okay? So initially this road was close to the polygons, but I just move it away. The shape of the road is still the same, okay? However, I've just moved it a little bit away from the polygons. Omit, I can decide that, you know what, based on my analysis, anything that is of a smaller area, these polygons, I can get rid of them so that I remain with only larger polygons. So instead of having 6, now I have only 3. Exaggeration. Exaggeration happens here on the road. So initially the road was just a single dotted line, but now I've increased the road width by exaggerating it and saying, you know what? This road is not just a linear feature, but it's a highway. So this is done especially during the symbolization of the objects. You can exaggerate the size of the road. So for those who have managed to stay with us up to this point, thank you so much. And as usual, go to this link, access the learning platform, and use the code to be able to access the course. I've also gone ahead and I've uploaded yesterday's video on YouTube, and I'm going to link it to the classroom just right away, and then we shall be able to have it available for you. So the video is about three hours. So you'll be able to have it in the class and listen to the recording of yesterday. I'm going to still do the same for today. We shall be recording. Please remember that we shall be putting assignments in the classroom, and these assignments will last up to next week. And try your best to make sure you complete them for every unit that we shall be handling. There will be an assignment. We'll give you some time to read through and respond to those assignments up to next week. Thank you so much, and I wish you a good afternoon, and thank you for staying longer with us up to this point. Unless there's a burning question, kindly let me know, and then I'll be able to respond. Thank you for that. Bye.
Thank you very much.
All right, thank you and bye.
Thank you very much. Thank you.
Thank you very much.
Thank
You're welcome. All right, bye.
Thank you.
Thank you.
Thank you. Thank you, Malcolm.
Thank you.
Thank you,
All right.
Chima.
All right. Bye,
Bye.
Eunice. Okay.
See you, sir. See you.
All
Thank you
right,
very much,
Manla,
sir.
Regan, Leon, Angelique. Wow. How do they pronounce this name? Angelique Nyishirimbere. Okay. The Rwanda. All right. The Rwandan
So
people
please,
have very
if you don't
interesting
mind,
name. Too long.
Sorry, please.
Okay.
Sir, please, I don't know if you're free. I got the link today from a colleague at my workplace, and I don't know if it's still possible to register today. The site seems to be down. I don't know if I can get some help with that.
The site is absolutely up. I don't think it is down. I can show you quickly here. It's running perfectly well. So maybe you had tried when you could have tried when the traffic was too high. So maybe you'll give it a little bit of time and then try again. But we have a WhatsApp group, so try to be part of that group so that in case you have any question, just post it there. We are looking at it up to the end of the day. You should be able to access the classroom.
Okay. Thank you very much.
Okay. All right. Bye and good afternoon, Ibrahim. Enjoy your fast. Me, I'm going to eat lunch. Sorry, you can come and share with me, but you have to fast. So yeah. All right. Bye.
Goodbye.